right time. Right. I think there has been problem with our sound as well, because I didn't listen. Recording started. Yeah. So speaker is. You can hear, okay. But I think the problem is probably with our speakers here in the seminar room. So let me call IT support. But anyway, we can keep going, because I mean, the audience here can listen to me. So and you can listen to me as well. So that is more important. So again, welcome to day 4, which is the last day of Asia Connect SDON training event. And I was just mentioning that there has been just a couple of changes in the program. So one of the talk has to be dropped by Ms. Hamida. On that talk was on the application of artificial intelligence and machine learning in optical communication. She had to move to her hometown because of domestic emergency. The first talk is still there. Ms. Gulmina Malik, one of the researchers in the SDON lab, she will talk about virtual passive optical networks. And then the third talk is moved back. Dr. Salman Abdul Ghafoor, latest research trends in optical communication, and he'll discuss more about radio or fiber, and probably touch some a little bit on the ORAN as well, Open RAN as well. Okay, so yes, thank you. Again, another mistake by myself. Screen was not shared, but anyway, yeah, that's on there. Okay. Can anybody say something, please, so that I can check the sound here? Just unmute yourself and say hello to us.
Assalamu alaikum, sir. How are you, sir?
Walaikum assalam, Mr. Ahmed.
Hello. Good morning, sir. Good morning. I am from Nepal.
Nepal, yes, Mr. Parajuli. Thank you, thank you both. Thank you both of you for participating in the sound testing. Thanks a lot. So yeah, it's yeah, morning Pong. So yes, I was speaking without sharing my screen. Anyway, thank you, Fazal sir. So anyways, right here, as you can see, the first talk by Gulmina on virtual passive optical networks. Second talk by Dr. Salman Ghafoor on radio or fiber. The purpose of these two talks, they might get a bit towards the research side, but because today is the last day, and so far what we have been discussing is mostly hands-on or stuff which was included in the training program to bring everyone on the same page in optical networking and software-defined networking. So I think before finishing off the training on the last day, we should touch upon some latest research that at least the researchers are being following in different research labs. So that's why these two talks are here. Then we'll have a visit of the Asia Connect SDON lab. The visit will be for both physical and virtual participants. We'll you can see things on camera. So definitely the lab is not in super presentable form, but it's a lab, it's a research lab. So the research labs are like that. The important thing is the equipment that we have procured thanks to the to this funding, and thanks to the efforts of the project management team of TN administration and Mr. Kim especially. So we would like to show you guys that equipment mainly. And then after the tea break, we will have the talk that we were not able to have yesterday because of the technical hiccups by Mr. Abdoulie Feller Nyang, open networking using Dockers and containers. And as per plan, no change in the final keynote by Professor Vittorio Curri. It is still there from 12 to 1 Pakistan Standard Time on open and disaggregated optical transport networks. Physical simulation environment, that is the subgroup of under the consortium of telecom infra project led by Facebook. So And then there has been another slight change because of the change in lunch menu. So the lunch time is for 1.5 hours, and we'll start the closing ceremony from 2:30 to 3:30, so 1 hour. And again, the closing ceremony is for both physical and virtual participants. So the virtual, we'll have certificate distribution for physical participants as well as virtual participants as well. So we have your virtual certificates ready, and so you all of the online participants should also please take part in the closing ceremony as well. Okay, so that's the program, and without further delay, I should hand it over to Ms. Gulmina for her presentation, for her talk on virtual passive optical networks. Okay, so Gulmina, over to you, please.
Hello and Assalamu alaikum. My name is Gulmina Malik. I am a researcher here at NUST, Pakistan. So I'm here to present a brief talk on virtual passive optical networks. Okay. So this is the outline of my presentation. Okay, before moving towards virtual passive optical networks, we're first going to let's go into the depth what PON basically is. So we know that internet traffic is at the forefront of driving modern digital economies because of the huge power, compact size, and tolerance to electromagnetic interference of optical fiber. Fiber to the home has been considered the perfect course of action for access networks since the invention of optical communication. Increase in the bandwidth demand influences the network operators to come up with innovative solutions for service provisioning in access networks. They are bound to expand their capacities and upgrade the services. The studies have proved that the bandwidth demand increases 6 to 10 times every 6 years. We know that copper infrastructure is limited by bandwidth and reachability. So PON is an attractive solution providing broadband services to the users. It is a point to multi-point fiber-based network. It consists of an optical line terminal that is a service provider situated at central office, a splitter, and a number of optical network units, which are user equipment for fiber to the home. The PON market is economic friendly because there's less power supplies required for it. The electronic equipment is totally removed, and the price of fiber is also very less. PON delivers high speed and high capacity network access to the end users, but at the cost of capital expenditure, which is CAPEX. So we know that overall it is cost effective, but the underground installation of POS is very huge, which hinders its large mass scale deployment. Okay, so this is an overview of PON. Here you can see there's an optical line terminal that is situated at central office. This is an optical splitter, and these are the ONUs at the customer premises. Okay, so let's introduce to XG-PON, which is 10 gigabit capable passive optical network. It is a standard defined by the Full Service Access Network Group of International Telecommunication Union. It provides a downstream traffic rate of 10 gigabits per second and upstream transfer rate of 2.5 gigabits per second, or 10. XG-PON has been well standardized for providing full services to the users with one optical network. Here you can see that between the OLT and the ONUs, XG-PON has been placed. Okay, this is an XG-PON network architecture in more detail. Where the OLT is lying at the central office, which is connected to the core network, and in front of it is a splitter or jointer that takes it to various ONUs and remote radio heads, right? And a long feeder fiber or like is used. It's basically reach extender, just taking it to longer distance. Okay, now we'll discuss the working of PON. For the downstream transmission, traffic is broadcast from OLT to the ONUs, and for the upstream transmission, a scheduling mechanism is required, which is known as DVA. I'm going to discuss the DVA algorithm in detail later. The transmission containers are the service carriers that belong to the same ONU that report the buffer occupancy report. This report is sent to OLT by the ONUs, and then OLT has to decide based upon those buffer occupancy reports that what or how much bandwidth is required and how much bandwidth to be allocated to the ONUs. Okay, so here you can see there's an OLT and ONUs for the downstream transmission. As I mentioned earlier, the traffic is broadcast to the ONUs in a time division multiple access manner, whereas for the upstream transmission, the DBA algorithm is required. So what will happen is that the buffer occupancy or the bandwidth demand will be presented to the OLT, and then it will apply an algorithm, then provide them their bandwidth demand in form of a bandwidth map. And then the ONUs are going to transmit in the next frame. Okay, so why is there a need to move towards virtual passive optical networks? So we have seen that the infrastructure and that since, okay, let me just say it. Okay, as you know, okay, the bandwidth, each frame is assigned to a specific ONU, right? And the infrastructure is installed in a single area, right? And a single operator. So infrastructure is not utilized to the maximum, as well as bandwidth is not utilized to the max. It's a possibility that in the specific area, the bandwidth demand is not that much, right? And it is providing it, and bandwidth is like unlimited. So bandwidth is being wasted. Then there is a restriction of authority to the network operators, which are not given the authority to provide as per their needs. Even though PON is an economic solution, but it is still hindered by the capital expenditure, which is the installation cost of fiber. Scheduling mechanism is controlled by the physical OLT, which is owned by the infrastructure provider. Okay, so now I'm going to introduce you to virtual passive optical networks. Before going into that, since we know that increase in bandwidth demand has triggered the service providers to expand their capacities, the service providers are prompt to take the most of buying network equipment while maintaining a balance between minimizing the expense and optimizing the bandwidth. So in order to reduce capex, the copper infrastructure, the PON infrastructure needs to be shared between the network operators. This sharing of resources is called virtual passive optical networks. It improves the economic sustainability that allows different operators to operate over the same installed fiber, and different services can now coexist, and different service providers can operate over that same installed fiber by sharing it. Each VNO has now the full authority of scheduling the traffic of its own traffic, whatever the requirements of its customers are. Each frame is shared, each frame is sliced, and it is shared between each VNO. Each VPON slice is basically provided to a VNO, and it is going to operate in that. So working of VPON. In VPON network, the VNOs are given the full authority to schedule the traffic and provide services as per the demands of their users. In PON, each XG transmission convergence frame, that is basically known as XGTC frame, it is assigned to a specific VNO in a round robin manner, right? Each operator is going to get its own frame. But in a VPON, each frame is being sliced and different operators are allocated portion of that slice to the operators, right? And then each VNO is basically going to run a DBA algorithm, that is a algorithm which is run basically to provide bandwidth, right? I'm going to discuss it in detail later. Each VNO basically is going to run its DBA of choice. A virtual bandwidth map will be generated by the DBA, which is merged at OLT by the merging engine and converted into a single physical bandwidth map for the whole upstream transmission. Okay, so here you can see it's like XGTC, different XGTC frames that are being shared between 3 VNOs in this example, right? So each frame is of 125 microsecond. The VNO1 is getting this much part of the frame because its bandwidth demand was this much. As per their bandwidth demand, they're going to get the specific portion of the frame in which they can transmit, right? And similarly, this will be VNO2, and then this will be VNO3, right? So this is the system architecture of virtual PON, where you can see there are different operators now, and each operator is running its own DBA algorithm of choice. Let's suppose there's an operator that wants to provide low latency applications the requirement of customers are low latency, which like gaming or anything like that. So it has to run a DBA of its own choice, whichever fits its customers, right? And VNO2 is, these VNOs are basically virtual network operators, right? It's going to run its DBA of its own choice. Each of them is going to generate a bandwidth map. Okay, this DBA is basically generating a bandwidth map, which is then merged at a merging engine. This is situated at OLT. This is basically going to be merging the bandwidth maps into final physical bandwidth map for the whole upstream transmission. Now the ONUs are supposed to transmit in their specific allocated slots. Okay, so let's see what DBA or dynamic bandwidth allocation is. It is an algorithm which provides bandwidth on demand in a shared medium, right? It has to be collision free to avoid conflicts between the transmission. A virtual DBA is a virtualization technique that allows each VNO to deploy its own virtual DBA algorithm on top of the PON infrastructure. What it has to do, it has to decide what transmission containers to serve, to maintain a guard band between the frames, which was also present in the frame I just shared. I didn't show it in my slide. Yeah, but it will be there. The guard band will be there. Okay, between the frames. It also has to decide the bandwidth size and the start time of the bandwidth allocation. Start to synchronize the. Each VNO will run its own DBA of choice independently. Each VDBA will collect the buffer reports from the ONUs and generate a virtual bandwidth map and deliver them to the merging engine. So this is the task of dynamic bandwidth allocation algorithm. Okay, it has 4 different bandwidth types. There's assured, non-assured, and best effort. Fixed is portion of the total capacity. It will be allocated to the transmission container 1, that is TCONT1. Will be available at any time required by the ONU. It will be allocated to TCON2. Non-assured is the additional bandwidth that is required, that is available if the entire assured bandwidth is utilized. It will be allocated to TCON2. The best effort is the additional maximum bandwidth that can be used by any ONU, which is allocated to TCONT4. Okay, in the different DBA algorithms have been proposed to fulfill the bandwidth the users. I've just write a few. There's Giant, there's XGiant, and then there's EBU. XGiant is the priority-based mechanism. XGiant is the refinement to improve its performance in terms of mean delay and packet loss. And EBU is efficient bandwidth utilization. It utilizes the unused bandwidth and overloaded TCONs. There are many other DBA algorithms in literature as well, owing to the demands of the users. Okay, so I'm going to discuss with you the merging engine now. Okay, so the merging engine is basically supposed to communicate with the VDBAs that are controlled by the VNOs. It has 2 main tasks. It has to pass the buffer report to the DBA and receive bandwidth map in return. The bandwidth maps that are collected from the VNOs are then merged at the OLT by the merging engine and converted into a single physical bandwidth map for the whole upstream transmission. This bandwidth map is then sent to the ONUs, which then transmit in the next frame with slot time and space provided. A capacity sharing mechanism has been used. This implementation of merging engine is done in Network Simulator NS3 using an XGPON module. Okay, so here it's a clear picture of bandwidth map. What is it? Is basically receiving different virtual bandwidth maps from different operators. Like there's an orange one, it's like from one operator, that's from second operator, it's from third, or there can be so many operators, right? And they're all going to be merged at the merging engine, and each of this a portion of this final bandwidth map will be generated in such a way that each bandwidth map, virtual bandwidth map, is going to be accommodated in that, so that all of them, all the operator, all the users can use that final bandwidth map to transmit their upstream transmission. Okay, this is the merged bandwidth map. It's a flow chart of it. What to do, it is going to get the bandwidth maps generated by DBA of the VNOs. It is going to append the allocation and final bandwidth map. Now it is going to check if the total size of the allocations is less than the XG-PON frame size. XG-PON frame size is basically 9720 words. It is fixed, right? So it is going to check if the total size allocations is less than the frame size, then there's no problem. It is going to give us or generate a final bandwidth map. All the allocations now, like they're all present in it, like there's no need to change anything, right? Because all of them have been allocated. But if it is not true, it is false, then what it is going to do is it is going to calculate the surplus bandwidth that will happen, which will be like it has to subtract the XG-PON frame size from the total size, and if the surplus bandwidth is less than total best effort. Okay, so why just best effort? Because okay, I didn't mention it earlier. There's a priority of these TCONs. The lowest priority TCON, or we can say lowest priority bandwidth, is best effort. The highest priority is assured, or like we can say fixed, then it is assured, then it's non-assured, and do in a total capacity, it is going to first assured portion of the total capacity to the users, then it is going to distribute the non-assured, and then the least priority, which is best effort. So it is the least priority. It is going to check if the surplus bandwidth is less than the total best effort. If it is true, then it's going to generate the bandwidth map by reducing the best effort allocations. But if it is false, the best effort allocations are more than that, what it will do, it will remove the whole best effort allocations, and it's going to reduce the non-assured because it's priority bandwidth. Okay, not going to discuss them in detail, but just a little bit. Okay, these are the simulation parameters that I used for my experimentation. To generate in realistic internet traffic, I used a Poisson-Pareto burst process with the Hurst parameter of 0.4. The simulation time was set to be 15 seconds, and the propagation delay was 400 microsecond. Distance between OLT and ONU was set to be 6. And then I used 16 and 15, and the maximum link capacity 2.15 gigabits per second. Okay, let's see. Okay, let's see. There are two operators, and both of them are running a single DB algorithm. Here I've used Giant for both.
Ganwise.
Okay, sorry. Okay, so if there are both two operators and both decide to run Giant or any algorithm, both decide to run the same algorithm. So this is the results that we induced out of it. Here you can see this is the assured, non-assured bandwidth, and this is the best effort bandwidth, right? Okay, here is also an example of a use case of three that are trying to run their DB algorithm, but all of them are running independent DB algorithms. Why? Because the bandwidth demands of all three operators is like each customer target market is different. So one decided to run Giant or EBU, and the third one decided to run X Giant. A result that we get out of it, that here you can see clearly the assured bandwidth of has the least delay, and the best effort delay because it is the least priority bandwidth, right? So yeah. Okay, I'm going to conclude it by I've implemented a merging engine for same as well as different DB algorithms to support multi-tenancy networks using network simulator NS3. Now the DBA is virtualized from OLT to a VPON slice, which is now controlled by VNO. Previously, it was controlled by the OLT or the infrastructure provider. Different DB algorithms and then tested to of impact choice of DBA by the operators. results have indicated the service performance in terms of packet loss and delay is affected by the operator's choice of DBA. Maximization of the bandwidth utilization by sharing of operators, this coexistence generates new revenue streams. Okay, so in future, we will extend this work to implement a cooperative DB and module. This cooperative DB is going to cooperate with the mobile scheduling and a work to support 5G front haul networks by network slicing based TDM PON by virtually isolating each subnetwork on the TDM. There are three types of traffic that are generated through network slicing to meet the 5G requirement. It's enhanced mobile broadband, EMBB, ultra reliable low latency app communication, URLC, and massive machine type communication. Okay, this is an architecture we drew for the future reference. We can see this is the OLT. This is our current OLT, right? Now, what we will do is also place a BBU in the central office and perform a cooperative DBA between the BBU and the OLT. And in front of the ONUs, we have placed remote radio heads that are going to provide traffic like URLC, it's providing MMTC, and it's providing EMBB. Thank you. Okay, thank you so much.
Thank you, Gulmina, for the talk. Very nice talk. So I would, if we have a couple of minutes before starting the next talk of Dr. Salman Abdul Ghafoor. So if anyone from the physical audience, yes, please, Femix sir.
Basically, you have asked me that by using a visualization, you are basically maximum utilizing the resource of any OLTs. So by using visualization, we can also achieve the functionalities of high availability. Let's suppose if I basically want to utilize two OLTs, I have two neighboring OLTs. I'm supposing that the traffic is going from one virtual OLT. If this is down, this traffic can be shifted to the other OLTs. So the communication between two OLTs by using a visualization can provide high availability in terms of active or active passive.
Yeah, but that will also require a lot of expense as well, right? Because the infrastructure is going to be like installed 2 times because there are 2 OLTs. Yeah.
It can be deployed.
Can 2 OLTs be deployed?
I mean, generally, it can be, but generally in the central office, because one OLT is able to support thousands of homes, I think. It can be. The quick answer is yes, it can be.
OLT is active components, not passive.
Yeah, but
OLT has many cars. Yes,
but sir,
already many cars, and you have the
backup within the same OLT available. Yes. So generally, I mean to say, generally, I have never heard of a model where in the central office 2 separate OLTs are being deployed, one as an active and second as a backup. There is only one. Yeah.
Because they have, I think, multi-level redundancy to be deployed in terms of power supplies, in terms of big chips, in terms of
yeah.
If whole box is down, then neighboring office OLT can be used to serve that area by using visualization.
No,
it's not possible
it's not
to extend the fiber from one OLT
Yes,
to
yes.
one area and then
another OLT.
Extend its fibers to that area.
Okay.
Especially
It's very costly. It's very costly. It's
Yes.
mesh network, and you spend all the mesh network twice.
Especially because an OLT is supposed to serve the users in its footprint, and the second is generally probably few kilometers apart. So I mean, it's 10 kilometers, maybe even more. So generally,
So reliability exists on the same box.
yeah. By virtualization, by the way, we don't mean to divide the power and all those things. Virtualization is only happening on the upstream frame transmission that Gulmina mentioned. So I mean, the upstream frame was previously, and this is just an idea. So the practical implementation is not there yet. But I mean, just imagine for the case of Islamabad, let's say, if Neatel has a fiber footprint, FTTH, and PON deployment is quite an expensive business too. That is why its large scale deployment is still hindered. You cannot see PON in the rural areas a lot because the large scale deployment is hindered by the upfront capital expenditure, which is still quite a lot. Okay, it's a good access technology, but it's the upfront capital is still quite a lot. So what we are trying to propose here with our colleague in Trinity College Dublin, Ireland. Basically, it's a mutual research topic. Is that by virtualizing the PON, what we can do is that we can have multiple tenants. So one is Natel, one is, let's say, I don't know, PTCL, another one is
Vateen.
a third company. We are short of companies here in Pakistan, but let's say Vateen has some access fiber. Which one?
Cybernet.
Cybernet. Okay,
From
let's say
Cybernet.
Cybernet. So the all three VNOs share the same physical infrastructure, but the owner of the physical infrastructure will be one of them. Probably, let's say in that area, Natel own the physical infrastructure, but the OLT is being shared. So each of the three VNOs will assume that, okay, this is my device, and I have a right to schedule upstream traffic of my user in that premises in that neighborhood. So this is the idea. That is why a merging engine is required.
Yes.
To merge the allocations of different operators and make a single allocation and transmit it to all the ONUs. Okay.
And every VNO basically has its own policies
Yes.
regarding this.
It can.
Yeah. And how these VNOs basically differentiated from each other. If there be any instance, VPNs will be running between all VNOs, how we can differentiate?
We are not certain about the use of VPNs here, but how you would like to take that question? How we differentiate is in the DB algorithm.
Basically, we differentiate it through different DB algorithms. Like their bandwidth demand of all of them is different, right? So their DB algorithm, which they are going to run, which is a dynamic bandwidth allocation algorithm that just defines the bandwidth demand of the users. So, but we differentiate through different DB algorithms that they are going to use.
Like, for example,
But
over
within
here,
the same VNO, there will be different requirements within the same VNO. We may have faced different requirements for the bandwidth for the different users. So each user will be also differentiated by DB algorithm.
Yes, again, that's the process internal to the DB algorithm. What actually happens is that we have to go into some detail of the process. What actually happens is that over here you see that the three different operators are running three different dynamic bandwidth allocation algorithms. One is running Giant, another one EBU, another one XGiant. If we dive deep into one of them, let's say what will be happening for Giant. So that VNO maybe has, let's say, 20, 30, 40 users. And what you're asking is that how will be their traffic differentiated?
Yes.
So that 30, 40 ONUs will be sending their, what do you call them?
Bandwidth map.
Reports, buffer
yeah,
reports, their buffer reports, and their buffer reports will be managed by the Giant running at the OLT. And then, I mean, what is being generated by one VNO is finalized bandwidth map, accumulating all the requirement of their own users. Okay.
But I think this is basically a more generically bandwidth allocation. This is bandwidth allocation is according to the user requirement. That this user required how much bandwidth.
Yes.
But like at the ISP end, some decision has been had to be made on the ISP end, like this user needs IPTV services. This user does not need IPTV services. This user subscribe for the 10 Mbps, 5
Perfect.
Yes.
Again, for that we have divided the traffic into different classes. So we have assured, non-assured, and best effort. Best effort is just like the least priority traffic.
This is quality of services. You can include that this is quality of services.
So what
You are allocating the bandwidth according to the basically quality of
requirements.
services, the frame in which you have you want this certain amount of bandwidth.
okay.
But I assume that in GPON network we are providing triple play services.
Yes.
On a single line, we are providing
Yes.
the IP telephony and IPTV and internet services. Let's suppose if a user wants to subscribe for only for the internet services, then how we can basically differentiate that? Because it is done, I think, by using multicasting.
Actually, in the downstream, it is broadcast.
It is broadcast.
Everything is going to every user.
Yes.
UPA is for
Upstream.
not for
Yes, not for down.
because the splitter downstream is splitting the power. Power is going to every user and they are reaching everything is to all users. But on upstream, we have to combine on the splitter that all the mechanism for the bandwidth allocation are for upstream, not for the downstream. No planning is involved at the ISP side. Downstream is the broadcast.
Yeah.
Okay, so we have Femi sir, thank you for your questions. We have a couple of questions from the online audience. So can we go for any ML algorithms instead of DBA? I have seen, as far as research papers are concerned, I have seen a couple of papers where ML algorithms are being used, but I cannot comment on how they are being used inside the OLT. And definitely what these kind of algorithms can be, what kind, I mean, can be any ML model, like any regression technique, or any a deep learning model like artificial neural network or something like that. I have seen them in papers, but I don't know, I cannot comment in detail that how they have used the ML techniques in the. Okay, so Lawrence is asking, is there any ways as SDON can be used in areas of in any of the areas? Yes, absolutely. Again, we have not included an SDN controller over here, but the role that merging engine is playing can very easily be played by a controller as well. And in fact, a controller will be in a better position to do that. So so the merging engine that we just displayed over here, this algorithm and this merging of bandwidth map can be done by an SDN controller as well. And again, I have seen research papers where researchers have been using this SDN framework to do this. Okay. So thank you for the questions from the online participants.
One
Yes,
comment
please.
From my side,
Yes.
distance standardized by the ITUT for GPON and IEEE for EPON is 20 kilometers, not 60 kilometers.
We have used it.
Because we are not using any amplifier. It's a passive optical network.
Yes, yes, yes.
And there is a power splitting. So the maximum distance which is standardized is 20 kilometers.
Okay.
And you have simulated on for 60 kilometers.
Yes, because I've simulated for XGPON, not GPON.
XGPON means extending the bandwidth.
Yeah, but
XGPON
in
is
the
10 G. GPON is for 1 GB data rate. XGPON is for 10 GB, not extending the reach. When
no.
we are going for the higher bandwidth, the reach
Okay.
is reducing, not extending.
Okay,
Right.
but I've read in the papers of XGPON
If
that
you see
it.
the standardization by IEEE and
Okay, in-
IEEE, they will
Yeah.
always mention the 20.
Okay.
Okay, thank you for pointing it out. We'll in the future studies we'll tone it down a little bit. Yes, please.
Can we use two similar algorithms, serial versions?
Yes, I have shown the use
Results,
case,
yeah.
the results
You
of
click-
that.
Will there be any consequences like interference or something like that?
No, because
No.
they both are running independently,
Yeah.
independent to each other, right? So there will be no overlap of them. Yeah.
So you said you differentiate these according to the algorithm. How are you going to differentiate them?
No.
No, actually, what I said was that relevant to his question, but both the algorithms can be same. Both of the bandwidth demand of these operators could be same. So both could be running the same DBA, but they are running independent to each other. They're not being running. They're running simultaneously, but independent to each other. They're not causing any effect on each other. Right here, you can see the results are superimposed on each other because exactly the same. They're not causing any effect to any of them. Right?
Because the DB algorithms are same.
There should be
Yeah,
some values who can differentiate both PMs. In firewall, we are using the same mechanism, virtual firewall, in which every basically instance is running its own VPN instance. Same time, some values will be used in that scenario as well, which can basically in totally independent both VMs.
Yeah.
And how we can avoid collisions?
Okay.
Very good question. Yeah. So
We have not considered any. First of all, we have not considered any for the simulation. This is just simulations. This is not like practically present at right now. We have not considered any channel losses, right? But these collisions are going to be avoided through the merging engine and the bandwidth DB algorithm. It's basically going to be the work of that DB algorithm and the merging engine, right? Which I have also discussed in this. That how the collisions
So
are.
I mean, if you go back to that picture, so I mean, if different virtual bandwidth maps, different VNOs have allocated traffic to their user within the same slots in the upstream frame, and there is a collision, let's suppose, then it will be solved on the basis of some policies and priorities. We have not. This is one area that needs to be further explored, because it was one of the very first work in virtual passive optical networks. So right now we have presented slightly simpler merging engine. Okay, so where we have not really, we are just solving the collision based on the fact that, okay, if it is a best effort colliding with the assured of the other one, let's keep the assured at its place and shift or schedule or slightly delay the best effort a little bit, just on the basis of priority. But in future we'll see that maybe how about the chunks of different VNOs? One should not starve the other one, so something like that. But right now it's very simple collision handling mechanism.
At the sport, we can use the verified queue as well.
Yes, we can. Absolutely. Yes, we can. Yes. Thank you. It's a nice idea. Totally applicable over here. Totally applicable. Okay, so I believe because we need to move to the next talk. Thank you, Gulmina, once again. This work that she just presented, she also presented yesterday in the Asia Communication and Photonics Conference in China. So well done, and thank you for your talk. Right. So without further delay, because Dr. Salman is here, please take the stage. No need to introduce you. My colleague here and associate professor at NUST School of Electrical Engineering and Computer Science. So his talk.
Okay, so hi everyone. Right. So the other day, I started talking about the optical communication system. I was not able to complete that lecture or that talk, I should say. So the first thing is to let's complete that talk. So we were going through the basic components of communication system. So a complete communication system, and so after that I'll touch upon the one of a special type of system that transmits radio signals from one point to another. So instead of coaxial cables or the copper-based cables, the radio signals, the wireless signals are being transmitted over the fiber that I'll discuss in the end of this. So the other day, we saw that if we need high data rates between switching centers or between the radio access units, so we need to use the fiber. We have these three basic elements, we can call them, of a communication system. So we have the laser diode or at the transmitter side, and then we have the fiber, which acts as the channel, and the photodiode. So we went through the different development of the year-wise development of different components that enabled the development of optical communication systems. So we saw that the main contribution for the optical communication, the fiber-based communication, was by the amplifiers as well as the wavelength division multiplexing technique. So once they were proposed, after that the data rates were increased by a huge amount. This was a typical attenuation profile of fiber, and we use this window, the C band, which has this wavelength range where the attenuation of the fiber is around 0.2 dB per kilometer. So we discussed the laser invention, then the optical amplifier. Previously, they were based upon electronic amplification, where we had to convert the optical signal back to electrical signal. And after that, after performing amplification, we would convert the electrical signal back to the optical one. But with the advent of optical amplification, this conversion process has been removed. Now all optically, the signals are being amplified all optically. So amplifiers were designed, initially proposed by these three researchers. So then we touched upon wavelength division multiplexing, that instead of transmitting each wavelength in a different fiber, we can and transmit them through a single fiber, because now the amplifiers, the optical amplifiers, have the ability to amplify multiple signals altogether. So when we'll study the amplifier after some time, we'll see that it has a large gain bandwidth, so it can amplify multiple wavelengths at the same time. So this is the progress of wavelength vision multiplexing and the different data rates that were being, and the different number of channels that were being added to the WDM systems. So then we discussed the fiber optic structure, which I have discussed later in further detail. So electromagnetic spectrum, in this spectrum, we are using, this part is for the optical communication systems. Generally, 1550 nanometer is being used for single mode fibers, and for multi-mode fibers, 1300 nanometer wavelength is used. So in optical sources, we saw that we need to excite the atoms, the electrons from their ground state and bring them to an excited state. After that, if there is this process begins with the spontaneous emission. So once the spontaneous emission starts, after that, we have multiple stimulated emissions, and that causes, it's a sort of avalanche effect, and that causes the generation of very strong signal, which we call the laser. So lasers are generally based on semiconductor devices, and in this case, the energy provided to the electron, in order to move the valence band to the conduction band is given by the external voltage source. So because the spontaneous emission also exists apart from the stimulated one, so that spontaneous emission acts as a source of noise, and that's why we have, the laser is not a perfect, it has not got an infinite OSNR. So there's always some value of OSNR because the noise always exists. Right, so then we saw the structure of a typical semiconductor laser. And so this is the transfer function where the input laser and output light is being plotted here. So these are some of the materials that are being used to develop laser diodes. So after that, we went through the optical modulation, where the direct modulation and external modulation. We saw that for direct modulation, the input signal, the data is superimposed over the bias signal. So we need to bias the laser diode with the application of a source, an external source. And if we superimpose the data signal, which is also an electrical signal, over the bias signal, then that's called the direct modulation. But direct modulation has a limit that it cannot transmit data generally higher than 10 gigabits per second. So for higher bit rates, we need to use electro-optical modulators, that is through the and to get the external modulation. So for external modulation, we can go, the bandwidth can go up to 60 gigabits per second. So the mainly used external modulator is a Mach-Zehnder modulator, whose typical structure is shown here. So this part is the optical waveguide. We divide it into two, and this gray portion is the electrical. These are the electrodes where we apply the data signal. So light input is modulated according to whatever data we apply to these electrodes. So this is how modulation of the optical signal is carried out. This is a typical of Mach-Zehnder modulator. So we use this linear region between these 2 points. Whatever data we have. So for example, in this case, we have 1, 1, 0, and a 1. So that is being converted into light. So on this axis, we have the electrical signal, and at the output, we will get the signal in the form of light. So then this signal, the modulated signal, is passed through a fiber. We discussed that through the process of total internal reflection, we can confine the light inside the fiber. This is this acceptance angle. It's a cone in which we need to align our input within this angle, the input light. Otherwise, if we move out of this cone, then the light will not be coupled into the fiber and it will, move out of the core. So we went through some parameters such as numerical aperture. They are dependent upon the refractive index of the core and the cladding. So this numerical aperture determines the allowable angle that you can use in order to couple the light into the fiber. So then we have the step index fiber and the graded index fiber. So finally, we saw that there are two major types of fibers. One is the single mode fiber. They are for longer distances. The core diameter in that case is 8 to 10 micrometer, which you can see is very narrow. So they are more difficult to design compared to the multi-mode fibers, where the core diameters are in this range. And the cladding is 125 micrometers. So the cladding for SMF is also around 125 kilometer. So multi-mode fibers are generally used for shorter distances and lower data rates, because the effect of multi-mode dispersion is quite high in these fibers, and so we cannot transmit the data to a longer distance. So generally they are being used for applications such as data center interconnects. The single mode fiber is used for very long distances, such as the submarine cables that we have. They connect the different continents that we have under the sea. So in this case, the loss is very low. The intermodal dispersion does not exist because we are transmitting only single mode of the laser. The only type of dispersion that exists is the chromatic dispersion of the fiber. So this is the fiber attenuation profile, where, as I mentioned, this is the region where we transmit the signal. We use this region of the fiber because this is a dB scale. So the attenuation over here is around 0.2 dB per kilometer. So the attenuation is very low. This is the lowest that has been achieved until now. So for transmission fiber, so this is why we use this range of wavelengths. So fiber dispersion is it happens in the single mode fiber when we input our signal. So it's, let's say, a data signal 1011. The pulses are broadened while they are being transmitted through the fiber. After covering some distance, the pulses broaden and they can overlap with each other. So at this instant, we can still differentiate between 1 zeros, but if this signal is further transmitted without compensation through the transmission fiber, the overlap increases and it becomes difficult for the receiver to differentiate between a 1 and a 0. So before that happens, we need to compensate the dispersion. So this is a typical dispersion plot of a conventional single mode fiber. So dispersion is composed of different components. So we have the waveguide dispersion and material dispersion. When we add them up, we get the final dispersion parameter D. For the 1550 nanometer range, the value of dispersion is around 16 to 17 ps per nanometer per kilometer. Right. So how can dispersion be compensated? We can use a fiber, a dispersion compensation fiber that has an opposite profile to the normal SMF. So it has a positive variation with respect to wavelength, and the DCF has a negative slope with respect to the wavelength. The slope is the values are much higher. You can see -300, -400 compared to the SMF, because we want to use a small piece of this DCF. This is a specialized fiber, so we want to use the as small length as we can for the purpose of compensation. So if we have a DCF in the link, what it does is if the pulse after transmission through the standard single mode fiber, if it expands, we can compress it after passing it through the DCF, and this is the output of the DCF that we obtain at this point, right? So the new discussion that we'll have is about optical receiver. So the receiver part is left. So we have gone through the transmitter that is mainly composed of a laser source and a modulator. And then the next we went through the channel, which is the fiber. And finally, we receive this signal at the optical receiver. So the principle of receiving optical receiver is quite simple as well. It's basically it's the opposite of the laser. So we have a photo detector here. Photo detection takes place. This process is opposite of the laser effect. What happens is if there is an incident photon, the incoming signal that we want to detect, this incoming photon excites the electrons in the valence band of a semiconductor material, which is our photodiode. This electron moves into the conduction band. So now this electron is free to move, and the number of electrons that we get depends upon the intensity of the light, right? So if we have a larger intensity of light, the number of electrons would be generated would be large, and these electrons contribute to the flow of current that we obtain at the output of the photodetector. So effectively, the process is opposite to what happens at the transmitter. With the variation of light, the electric current varies, and so we can detect our signal. We can obtain the data at the output of the photodetector. So basically, it's a simple PN junction. As always, it is reverse biased. So the electron that is generated as a result of this process. So the electron that we have in the conduction band, that is attracted towards the positive terminal of the external voltage, and this makes the current to flow in the complete circuit. These are some parameters commercially, that if you buy a photodetector, these parameters would be mentioned on it. So first one is the responsivity. The unit is amperes per watt. So that means the amount of current generated per watt of the. So we want this, as you can see, we want more current to be generated for any specific amount of input power. So because if more current is generated, then we can easily detect our signal. So the commonly used material for this is the indium gallium arsenide. It has a high responsivity of around 0.9. For the specific wavelength of 1550 nanometer, somewhere here, that we use for the purpose of communication, right? So we have these, the other material, silica. So you can see it has a small responsivity compared to this material. In fact, silica does not even give any responsivity in the telecom window that we are using. So this cannot be used for the purpose of photo detection of 1550 nanometer signals. Germanium can also be used, but again, its responsivity is much lower than this material that is indium gallium arsenide. So some parameters. Now, bandwidth is an important parameter because it determines the highest bandwidth signal that you can detect. So for example, if a photodiode, if this receiver is designed to detect 5 gigabits per second signal, and now if it receives a 10 gigabits per second signal, so it won't be able to detect it. The output would be distorted. So this bandwidth depends upon the width of the depletion region, as well as the width of the whole diode. So P and N type diode that you are using. Now, the generally commonly used diode is the pin diode. If you buy a diode, you will see they'll call it a pin diode generally. The reason is because of its structure. So it has a P-type material, and in between that, it has an intrinsic material. Means it's an intrinsic semiconductor without any doping or very, very small doping. and then we have the N-type material. So based on this structure, it's called a PIN photodiode. The intrinsic material is added in order to increase the amount of current generated when light is incident on this diode. So you can see this area is extended, right? So if you have more area of the intrinsic material, there is more area for the light to fall on, right? So number of electrons, and this is how the responsivity of the material, the number of electrons generated per watt of incident light will increase. So this is a benefit, but a disadvantage is that the length of the photodiode increases and that will decrease the bandwidth. So there's a trade-off between them. If you want a high bandwidth, your photodiode will not have a high responsivity. Its responsivity will be reduced. If you want to increase the responsivity, means you want more current at the output, then the bandwidth will be decreased. So there's the design of this structure. This is a typical structure of a PIN photodiode. This is the intrinsic material, the P-type material, and the N-type material. Light falls from this point. Electrical contacts are shown in the black color, this one and these two. So they are connected to the external source. So since this is a reverse biased material, so the positive side of the battery should be connected here, the negative here. As soon as electrons are generated in the intrinsic region, they are attracted towards the positive side and a current starts flowing in this circuit. You measure this current. Based on this current, you can determine what electrical signal was being transmitted at the transmitter. So then finally, another important component of the optical link is the optical amplifier. This amplifier is mainly based on the erbium dope fiber amplifier. So erbium is a rare earth material. It's an element. So with a normal silica fiber, you mix erbium in order to make it amplifier, right? So the structure of this amplifier is very simple, but it's very effective. The reason why erbium has been chosen is its suitable energy states, meaning that we have this is the energy diagram for an erbium. We have at the ground state, let's call it E1. We have different electrons in this state. Then they are excited by a pump. So whenever you have what you call it, an erbium dope fiber amplifier, it has an internal pump as well, a laser source that excites these atoms. They move to a energy state E3. This state has a shorter lifespan, so the electrons or the atoms quickly jump back to this one, right, from E3 to E2, and after that, this region, when they jump back to this E2, obviously they would be emitting some energy, and that energy is not in the radiative region, so it's means it's not in the visible region. So when it reaches this E2, here the time it stays at this level E2 is much larger. So incoming signal, so let's say we have an incoming data signal that comes here, it stimulates this electron and it comes back to the ground state. During this process, it generates another photon. It gives an energy, obviously, so that's in the form of a photon. And the important property is the newly generated photon is exactly the same as the incoming signal, right? So that's how we have, if two photons at the incoming, you can see here we have more than two at the output, and so amplification takes place. This is a typical structure of the erbium dope fiber amplifier. You have the signal input that's coupled with the pump laser. This is the pump that takes the electrons from the ground state to the excited state. This is the erbium dope fiber, and at the output, you take out the amplified version of the signal. So this is the gain bandwidth. means that the region where the gain means that gain is plotted against the wavelength of the signal. So you can see in this region, that is the 1550 nanometer region, the gain of the amplifier is highest. So that's why we use it generally for this purpose. We also have another type of amplifier that is based on semiconductor. It's the semiconductor optical amplifier. The principle is the same as the semiconductor lasers, except that for the laser, the side walls, they are reflecting, right? So, but in this case, the reflectivity is very small, so that the light can, pass from one point to the other. So that's how the semiconductor optical amplifier works. So I've just been, how much time do I have? Okay, so I'll just try to, so this was the discussion of a complete optical link starting from transmitter. Then we have the channel, which is a fiber, receiver, and an optical amplifier. So I'll just finish my talk in 5 minutes, and we'll discuss an emerging area, that is the microwave photonics, where the microwave signals or the wireless signals are being transmitted over the fiber. So microwave region is, it starts from 300 to 3 megahertz to 300 gigahertz. So for example, if previously your Wi-Fi signals were being transmitted over a copper link, like a coaxial wire, you can now transmit it through the fiber, right, over the fiber using the microwave photonic techniques. Basically the link is almost the same. We have an electro-optical conversion that takes place here. So here we have that wireless signal which you want to transmit from one point to other. After the electro-optic conversion, the output light is modulated according to the input signal. So now this light can be transmitted over the fiber, and then we can receive it here, amplify it, and we try to obtain this output as close to this input as possible, right? So there are some distortions by the link, but we try to apply different processing techniques to remove this distortion. If you want to visualize this, we can use a direct modulation. It's called analog modulation because the wireless signals, they are generally in the analog form. They have a carrier. For example, if we are talking about a Wi-Fi signal, so the carrier in that case would be 2.5 gigahertz, and the data is being modulated on that carrier. So now that Wi-Fi signal can be applied to the bias voltage of the laser, and the output will vary according to the input or the wireless signal that you want to transmit. We can, it's opposed to the direct digital modulation that we have seen, where we only have 0, 1 and 0, 1. In this case, the analog signal will have any value between two limits, right? So why do we, let's come on to the point, this one, finally. I'll just finish off with this slide. So when is the optical transmission of the wireless signal more beneficial? This plot gives us the idea about that. So we have distance on the x-axis. You can see a fiber link has a loss. It's a constant loss almost. The loss increases by a small amount. That's because of the very small amount of losses due to the fiber, 0.2 dB per kilometer. The rest of the link loss is the modulatory losses, the coupling losses, all of them are considered here, right? So if the distance is high, the distance in fact is small, like we are in this region, then you can see the fiber link loss is greater than the loss of the coaxial cable. So if the distances increase beyond this point, then the loss of the coaxial cable becomes higher than the losses of the fiber. So after this point, it's you can see more suitable to use the fiber instead of a coaxial cable. So the time is almost finished. So I'll end my talk over here. If you have any questions, you're most welcome to ask. I'll try to answer them. It seems there are no questions, so I'll ask Dr. Aslan to take over.
Dr. Abdul Latif.
Ji, sorry.
So,
Yes, please.
These links will not be used for non-verbal communication. I think you are suggesting these links further.
That's correct. So it's, for example,
It will not provide higher bandwidth.
because yes, the wireless links, if for transmission of wireless links, the lengths are small. They're generally, for example, within a city. So if the let's say a telecom operator is a signal, we have a base station over here as well. So if he wants to bring his signal from the main central unit to this point, like this sector, he can do it through this fiber. That would be more feasible. But it's not for like the submarine cables or like that. Okay, thank you, everyone.
Right. So, thank you very much, Dr. Salman, for the talk. Now we are short of time, but let's do the lab visit and the tea break together. So the physical participants can accompany Mizna, and Mizna will take you to the SDON lab. Okay. And for the virtual participants, we are going to have you with us via video. Okay. So what I'm going to do is that I'm going to make one of my researcher in the lab co-host, and she's going to turn on her video, Afira. Okay. And then you will have the the lab is just 30 seconds away from here. Okay. So you will have the online have a view via video. I mean, that's the best we can do. So yeah, sure. If you want to have go for lunch, please go ahead, because after the lab visit we are going to have a tea break and we will reconvene. So I mean, from the physical or from the online participants, those who want to stay with us for the lab visit, that would be good. We're going to show you the rack where we have deployed the equipment, Lumentum and Cassini, and thanks to the Asia Connect funding. And obviously this equipment, we are going to tell you how it can be available for all of you, for all the Asia Connect partner and RENs. Okay. So so please, if you have any other commitment right now, I know the timings are different, go ahead for that, and then you can get benefit from the recording. Otherwise we are going to show you so in just a few seconds. Okay. So yes. Okay. Okay, so I'll see you guys after for the next session after I don't know, about 30 minutes at at 11:20 over here. Okay, for the session with Dockers and Containers Open Networking with Abdoulie Feller Nyang. Okay, right. So let's have a lab visit and the lunch break as well. Sorry, and the tea break. I'm really sorry. Lab visit and the tea break. Okay. So. Right. So if you, this is our campus, and this is the software-defined optical networks lab. And, yeah, you can show the online participants this track. I mean, that's all. That's pretty much all it is. So we have it's a point-to-point open optical line system, right? So all in the same rack. So we have the transponder over here. That is the Cassini from S2. And the transponder is point B. Again, Cassini, and by S2 is the name of the vendor. The product name is and the line system is by the vendor. Vendor is the name of the vendor, and the product name is rodent. And then in the middle, it's still missing. We should and give off to have fiber tools and optical emitters and optical spectrum analysis to do this. So, I mean, this is pretty much it. It's an open optical network, and this equipment costs us and cost Asia Connect 70,000 euros. So this is a 70,000 euros. So, I mean, regarding technicality, yeah.
Yes, so basically, the Cassini device we have here is more fun. Which means it actually takes multiple times. As you can see right now, we have a elemental DCO model here, which is connected to this. So the what we are working on right now, we find that it's an open box, which means that all the communication. So this Cassini device already comes configured with the ACO 400 model of the Acacia. But the fact that we are using a DCO model, then we have to derive that. We have to build a loop time, what is called a loop time, which is the library for communicating this transceiver to the actual Cassini device itself. How this device works is, now that we have the Cassini device, in the Cassini device itself, we have an operating system, the Open Network Linux. So with that Open Network Linux, we have Stratum embedded in it. Stratum is the tool we will use to communicate from the Linux hardware itself to the transceiver. So each transceiver uses a library for libtype. So those are the libraries that we have to build, because for the fact that it's a MOX folder, it has multiple transponders, multiple transceivers, and each of them has their own configuration. So the Cassini gives us that effect to actually communicate. Even as you can see, I will upload that. It's the momentum DCO model, which will be communicating to this momentum DCO model. But I know you are from the telecom agency, so you already are well equipped with that. But what we are facing right now, the issue we are trying to solve right now is building the Thai library that communicates this DCO model to this DCO model. And the fact that it's a MOX folder, it also comes with what is called the libtype MOX, which can be built to actually dynamically allocate different transceivers based on to allocate different transceivers dynamically. So yeah, right now, as we just said, we're stuck with trying to configure this transceiver here, which the one we have here. And this is a 200 gig MOX folder device here. So I think that's the bare-bone explanation of it at the moment. What we are trying to depict later is we will try to emulate a long-haul network, which was an 80 kilometer long-haul network. So we have fiber spools in the middle, and also we might also add an attenuator for noise generation. So actually emulate the actual long-haul and noise that's implemented in a fiber system, fiber system, optical network system. But what makes this good is when we are talking about like this, does the conversion, the momentum device here, does the conversion from electric to digital. Now, as we all know, the difference between ACO and DCO model. But the Lumentum device here, these Lumentum devices, they are the ones that have the reconfigurable ad hoc multiplexers. So they will be doing more like the switching in the optical network, while this will be converting the electric to optical signals here. So the best part of using this open source variable devices, the configurability we are talking about in optical networks, as it gives you that edge to not just be the vendor looking part of it. So once you can like we have what's 15 days ago, the company that created their own
Edgecore.
Edgecore actually managed to create their own lip type, which works with the transceivers. But then the fact that it's proprietary, we couldn't actually get them to sell us the.
No. The software for this lip that is provided by IPV.
Okay.
But that software alone costs 30,000 euros. So the point is that I mean we have got the equipment, but now I mean after getting the equipment, its deployment and then just getting it up and running becomes. So this is something good about the experimental research, that you can do many things on the simulator, but when you get the hardware yourself, you start thinking that I mean you cannot think of problems which can even become masters of PhD thesis. So, I mean just writing a lip type for this one, because what these two guys are doing right now is writing a 30,000 euro software. Okay. So because we don't have 30,000 euros, we have got the equipment thanks to the funding of Asia Connect. That the equipment alone costs 70,000 euros, but we cannot have a 30,000 euro IP filler software to make sure that these two are up and running. So we have deployed it, but to get it up and running, now we are trying to get open source software ourselves. What we are going to do is that we are going to take lead from the Acacia lip type, right? That's the
Same module, but it's an ACU module. This one we have a
is
DCU
a DCU module right here. And it's from Lumentum.
Yes.
The lip tie available open source online is not of Lumentum. It's an ACU module from Acacia. But anyway, these two are trying to get leads from somewhere. Whenever they are done writing the lip tie, we can patent it or not? We can patent it. I don't know. Sir, can we patent it? I think we can patent it. Right? I think it will be something quite good. Yeah. So this is pretty much it. Still exploring. I mean, the people who were talking yesterday are way ahead of us. But even our Italian project partners in Santana Pisa, even they don't have this device in their lab. So this is quite a niche product. They have Lumentum as a line system, but they don't have Cassini. They have its previous version, which is Voyager. So they don't have Cassini. So I mean, it also opens up possibilities of national collaborations as well. I mean, so we can, so just this is pretty much it. Just feel free to have any question, and if you would like to collaborate with us. For the Asia Connect partner members, we are working on a remote connectivity tool that is also part of the project. So what we are going to do is that with the help of that remote connectivity tool, this equipment and the resources of the lab will be available for the Asia Connect partner members, so that if you want to, sit in Bangladesh or Nepal or Bhutan or wherever you are and want to use the facilities, obviously with our mutual agreement, it will be available via this remote connectivity. So definitely, it's an open call for collaboration to national and both international partners. Yeah,
every aspect of it is open source. Like literally, we installed an open source trading system.
Yeah.
We installed an open source switch abstraction interface of it. And also the lip time we build is also open. So it means that for a telecom giant, it gives you limited flexibility. Just using this open box switch devices.
I mean, just imagine these devices are used to be complete black boxes.
a single vendor. Hardware, software, vertically integrated, one single vendor solution. You don't know what is inside the device. Now, what you have is a bare metal. You can play with it like a toy. Yeah, they're playing with it. Okay. So that's something that it's just like you have a PC and then it's just bare thing. You install your own operating system, whatever you want to install your own configuration. You want to go for dual boot, you want to go for whatever software. So this is an entire bare metal piece of hardware. Okay. So it's challenging as well. But there's absolutely nothing inside. Okay? Absolutely nothing. But it's good as well because it's open up. So that is what the open optical networks we have been talking about.
Right now, what we are working on is the fact that we have the configuration, the drivers for the ACO model. But the fact that we are using a DCO model, it already has the digital signal processing embedded in it. So we are trying to reverse engineer the ACO module and look at the registry markets with the ACO module to the actual hardware fabric that we have in the switching fabric, and also look at the registry market of the DCO module itself, and create all the C header files, because the operating system we're using here actually uses C header files for the embedding. As we all know, so we're reverse engineering the ACO module configuration and then looking at the registry markings and trying to use those markings with similarity, because with the DCO module, we embeds the digital signal processing. There are a little bit more differences. And also with different vendors also, they have their different vendor capability. They have their own proprietary parameters that different vendors. So as we're using the momentum transceiver, which anyone else can have a different transceiver with different vendor parameters here. So that gives you much more programmability to actually configure your end-to-end optical network the way you see it.
In fact, we ran out of project money, but if in future we can, because this is a 6,000 euro piece of hardware. That is a 12 lakh module, 12 lakh Pakistani rupees. So if we can somehow have funding in future, we have 1, 2, 3, 4, 5, 6, 7 slots available. Total 8. So I mean, this is again the notion of openness and programmability is right here. You can have the different module from a different vendor over here, a different module from a different vendor over here, and then over here. What Professor Andrea was showing in the slide yesterday, the partial disaggregation.
Yeah, this is a partial.
This right here is a partial disaggregation.
Because we have the and then the best part of it after we done all this ISO is like this whole system will be connected to an SDN computer. So meaning now instead of just having to manually configure everything, that programmability aspect of it can be added to, which means we can access each and every parameter of this device, whether it's the signal ratio, whether it's the host, whatever we want to configure itself, we can do it dynamically. And that alone, what it brings also is, instead of just using the in-depth knowledge we have of networking, we can integrate machine learning to actually study the network. Because now the machine learning algorithms that we'll be using will be talking directly to the controller instead of having access to this device. And most of the times in the industry, what we face is in the fact that if we have multiple vendor devices, we are faced with each device having its own configuration. So we would have, I think, that an all-around knowledge of an all-around system that can compose of all the configurations. It's like if you want to configure the edge network, you will have to use the user interface of the vendor devices or vendor hardware that are embedded in that edge network. If you want to use configure the devices in your access network, you have to use those vendor devices, those vendor locked-in devices that are configured. But with this system we have in place, it's like from the top, from the access to the edge network to the core network, all of it is integrated. And then all of it can be configured from the SDN control. And one might say that, okay, then that might also was a central point of failure. But then the programmability we're putting in it, and that openness means we can even use multi-cluster operating, multi-cluster SDN control. Like we said, even though we talked about it, that these SDN controllers are not yet very mature, but they are much more developing and faster in the networking industry that we expect. And looking at the data centers of Alibaba. Alibaba itself, from studying from their paper that they published, they are actually using partially disaggregated. And they ended up, because of the fact that this programmability is embedded into it, they ended up having their own custom-made in-house built management system for all their devices. And then now, what they're doing is they're embedding machine learning into it. So instead of, okay, let's say you have in your core network an issue, instead of your administrators or your engineers having to manually be alerted, you can have your machine learning algorithm depict the fact that, okay, let's say there is going to be a fault in this fiber optic, so it has already reverted to the secondary fiber line or secondary. That's the advantage that this gives us, this openness that we're using. So basically, it's a big thing.
So that's pretty much it. I mean, apparently it's just a point-to-point link, but actually it's a point-to-point open optical link, which is something pretty much new. So, there are any questions from anyone? I know that I have delved quite deep into the technical details as well. So, but even at the abstract level, if there is any question. Sorry to the online audience, I think they are complaining about the voice because of the sound that the TV is producing. That's that noise actually. So I think that's the session. That's pretty much it. We can go to the tea break and then we can take a tea break and we can reconvene after 10-15 minutes. Okay. So Abdoulie's talk has been shrinked. He was already talking a lot. Thanks for the nice demo. I couldn't have covered this in much greater technical detail, just like Abdoulie did, because these are the two guys who are actually knows this equipment better than anyone. I mean, I don't know. Yeah, they're writing this. Matteo Rahman is our PhD scholar. We have the talk because also working. So the controller is being hosted on the server. I mean, in the form of VM, Docker container, whatever it is.
Yeah, as right now, the most matured SDN controller we have is the owner.
Oh no, yeah.
So one might say, okay, instead of just having to host it on a VM, why host it on a Docker container? Because that was what network is going to do.
Yeah.
So it's like hosting it on a Docker container here. The limit, the ability to give you the configurability of it, and also the portability.
Yeah.
Because hosting it on a Docker container doesn't just mean like you can have multiple clusters of the operating system on different Docker containers. And they'll find that Docker supports all different aspects of networking, which is you can attach it directly to the host adapters, or you can create a network of its own. Because you can have multiple Docker containers, and then you might want some aspects, some clusters of your operating system, of your SDN controller to communicate, while all the aspects of your Docker containers should not be part of that network. And Docker gives you all this ability. And also, what it does is it allows you to build your own network. It allows you to configure and build your own network and relay as in how you want that network to function. Those are just the effects of it. So it's like using a Docker container for the owner's controller. Even if we have a downtime, we can just provision a new container. And then they find that Docker has an SDK, which brings in the programmable aspect of it. We can have multiple Docker containers, provision, and the owner's system running. And the best part of Docker in this sense is, let's say you have this in an example format. Let's say we have this operating system, but then the owner's that we're installing on it, which is the SDN controller, has some configurations that we already have. Let's say we've installed MMAP and we've installed all the softwares on the Ubuntu 18.04. And now we are shifting the system to a different Linux environment. We do not need to do all that configuration again. We just build a Docker file. Now that Docker file is what you will push to whatever repository you have, whatever private network you have, and then any other engineer that's actually implementing that controller, all he or she has to do is just run the Docker file. And it brings in all the dependencies again. So it brings it back that reliability that we have with Docker. There are multiple other container options that you can look into. And also Docker has its own enterprise editions, which will give you 24/7 support from their technical team, so on and so forth. There are other containers also, like the Kubernetes, which you can look into. But all these are just the advantages we have with this openness that we are talking about. And as we can see in the market right now, the tech giants themselves, they are all moving to disaggregated networks because of the level of customization it gives you and your network. I mean, you look at Google, you look at Alibaba, which have like the greatest customer premises. They have the greatest user bandwidth and allocations. They are all partially disaggregated networks. So actually jumping into or actually using it gives you the programmability, the stability, and also that end-to-end configuration ability of your network.
Thank you, Abdoulie, for a very comprehensive demo. Perfect. So, I mean, this is it. We can move to the tea break now. We can have a 15 minutes break and we can reconvene again to listen to Abdoulie, but not on the optical aspect, on a different aspect. Okay, so Dockers and containers, their benefits at 11:30 Pakistan Standard Time. So you have just shortened your talk. Okay, you have spoken for 15 minutes here, and now you have 30 minutes after the tea break. Right. So let's reconvene the online audience. Let's reconvene after 15 minutes. Okay. Thank you. Thank you.
of underlying open and underlying openness of underlying code to the community. Because why we are talking about this openness is for these source codes of this, because most of the times the proprietary hardware that we have, the source code, how it's implemented, it's not seen by the general public. So even its integration, its provision, or its development, it's lagging because it's always fixated on the technical team of that particular vendor that's providing the hardware. And a quick talk of the Open Networking Foundation. This is like a non-profit organization centered around promoting an open and collaborative community around the idea of open networking. ONF develops software-defined standards for open networking. Classification of these standards include the following: the technical specifications, because they had like a generalized, the technical specifications, which includes the framework documents, protocol definitions, information model, and component functionalities. And also the technical recommendations, which defines the APIs and protocols that will be used the seamless integration of the network architectures. And informal, which uses like case studies, use cases, white papers, and testing from various members of the community. Now, for the business aspect of it, like this is a forecasted market share, which said 73 billion in revenue is expected to ship to vendors delivering ONF-based solutions to operators. Open Networking Foundation-based solutions to operators. And we can see on our domain, which is the optical transport, there is going to be a shift of 9 billion to it. So it's a matter of, it's not a matter of whether it's coming, but it is already here. As the market and the CapEx part of it, it's increasing on a regular. And this forecasted market share was on 2021. So now we come to why Docker containers and not virtual machines. And just depicted from the image here, as you can see, the virtual machine comprises of the infrastructure, which is the bare metal or the hardware. Then sits on top of it is the hypervisor and the ghost operating systems. Anytime you create an operating system on the virtual machine, it's not it's like it creates a guest operating system on top of the hypervisor, which is there for dividing the network hardware, dividing the hardware of the computer to the various guest operating systems. But with Docker containers, it's a different ideology. The Docker container or the container engine sits on top of the operating system that's embedded in the machine you've already had. And then from that, it creates multiple bins, libraries, multiple containers on top of that Docker engine. So Docker with open networking here, like the rapidly growing server, why is Docker actually needed in the open networking field? Like rapidly growing server virtualization, especially in open networking and cloud services, are some of the trends leading the industry, networking industry, to start focus on disaggregated network architectures. And many companies these days, as we all know, are aggressively adopting Linux containers because they are a collection of isolated processes that can handle unexpected increasing application workloads on top of the Linux operating system. And Docker, the company behind the Docker container runtime, came up with the container network model. Around the same time, CoreOS, the company responsible for creating the RKT container runtime, came up with the container networking interface. These are just different programming interfaces that communicate with the network hardware of any barebone hardware that we have in place. But as you can see from the note, this talk would be focused on Docker itself. So what does Docker provide? As the collaboration, modularity, and scaling, and the mobility, the ability to run. Because as we said, in the fact that Docker itself, the containers, they do not sit directly on the operating system, but they sit on the Docker engine that is on the operating system. Meaning, if you have the same kernel running on multiple operating systems, the same kernel on different operating systems, then you can install the Docker image on each of those, and then it will be uselessly and unexpected of the operating system it is running on. And the flexibility, like if you need to perform an upgrade during a product's release cycle, you can easily make the necessary changes to Docker containers, test them, and roll out new containers. So the Docker momentum, as of 2021, there had been 450 plus Docker EE commercial customers, which is the enterprise edition, 37 billion container downloads, job listings on LinkedIn, 3.5 million Dockerized apps and active 200 plus active Docker user group. It shows that Docker is not going anywhere, or it's not just an up and coming technology that will just die out in any moment. How does Docker work? Like Docker packages an application on all its dependencies in a virtual container that can run on any Linux server. That is why we call them containers, because they have all the necessary dependencies contained in a single piece of hardware. Like with Docker, it's composed of these two main, which is the daemon, or called the Docker engine, which is used to build, run, and manage the containers, a high-level API, which allows the communication with the daemon itself, and a CLI client interface. This interface we use to make all available, all this communication available. Just what I've just explained right now. So this is just a bare image of Docker, and then how it's how it stacks up its hierarchy here. As you can see, you have the bootfs, or the kernel, which is the underlying kernel of the operating system. Then you have the base image, and then you can have multiple images, which are then used to create a container. Now, this was just a quick demo. This is just like a quick line put on Docker, which just shows, okay, how Docker runs itself. Like when you run this command, these are the following things that happen. So just to go back to the demo, I would want to go and use my Linux kernel, my Linux command line here, and just show you like the basics of Docker here. So after installing Docker, as there are so many ways of installing Docker, you can have the deb file, which is the Debian file, which can give you installation process, or you can install it from source the way you want to install it, and with all the dependencies, and actually having the source code file, or you can follow the install instructions from the Docker website itself. Now, if you've ever used ONOS, which is the Open Networking Operating System, you know it comes with a lot of dependencies. And these dependencies include having to have Java virtual machine on your PC, having to have multiple other dependencies that it uses, like let me show you here with the okay, these are the ONOS requirements that we have here. As you can see, it has these port requirements, it has these Java requirements, and all of this. So why would you need to use Docker? Instead of actually installing all of these on your system, let's say you're using OpenJDK, which is a Java version of 11, and you already have another Java version of 7, which is used by another application on your system, or JDK 8 or any of that sort. What Docker does for you is it gives you that abstraction part of it. Instead, all of that application is embedded in a container. Like the first command I would show you here is what is called Docker images, which will show you if you have any images, sorry, as it is, it uses root privileges, so I'll have to use the sudo. Let me just, yes. So when I run the Docker images itself, it gives me all the downloaded images that I have. So let's say I wanted to download the ONOS SDN controller itself. Instead of having to install it manually on my PC and run it on a Docker container, all you need to do is just go to the Docker Hub. You can just, oops, sorry. You can just you can just go to the Docker Hub, which is hub.docker, and then download the ONOS rep ONOS image. And you can do that by just calling the Docker pool ONOS project /ONOS. And what this does is it pulls this repo. It looks for it on your system. If it's not available, then it pulls it from the Docker Hub. So I've already done that step, and now I have it here. That's why when I run the Docker images, I can see the ONOS project ONOS. So to run this command it's here, to run this image here, all I need is Docker run IT, which means I want to run it in interactive mode. And then minus -D, which is detached mode, meaning I want it as a background process instead of it running on the terminal directly. I want it to run as a background process itself, and call the, and give it, let's say I can use the name tag also. And what it does is, because every time it gives it an ID, and this ID, and also instead of running, just run the ONOS project. So you can see /ONOS. Okay, so when I do a Docker ls, I will see Docker ps, I will see all the Docker processes that are running. So as you can see right now, okay, let me just remove this one. It was running for a while. 7D, 5D. Okay, as you can see, it's giving me an error response right now, which showing that you cannot remove the container. It first has to be stopped. So what I can do is just force remove it. 7D, 5D. Okay, because it was an already running container. So if I showed you Docker PS, which shows you that the owner's container that I just ran previously is already running. But the issue we are facing right now is in terms of, let me, okay, so now you can see it better. Yes, the issue we are facing right now is, okay, now it has a list of ports it uses. This is where the Docker networking comes into play. Now it has a list of ports it uses, which means it needs to listen to port 6640, 6653, 8101, 8181, 9876. Now with Docker, what it gives you is it gives you multiple networking, multiple ways of handling networking. As I can show you here, the way is you can either set up a bridge network, which is the default network driver if you don't specify any network, or you can set up as a host for a standalone container, which means the Docker itself, the Docker container attached directly to the host network, which means whatever port it uses in the Docker container, it's attached directly to that port on the host container. Or you can use an overlay network that connects multiple Docker daemons together and enables swarm services to communicate with each other, which is more like you having a swarm or having a group of containers all on one network. Or what you can use is a MAC VLAN network, which also allows you to assign a MAC address to a container, making it appear as a physical device on your network. Or you can say, okay, I don't want any networking on this device. So what I will want to do here is, as I run it like this, if I were to go to this, with the owner's controller, it uses the 8181 to communicate with the UI. So if I were to use the, go to the IP 172.17.0.2, it's not responding. And the reason being that I didn't attach any of these ports. I didn't attach any of these ports to the container. I didn't map them to the host. So what I can do is actually just remove this container. I can remove it forcefully, or I can stop and remove it, but just remove this container and then run it again. While I can also say, instead of just running it directly, I can run it and give it the network parameter. And what I do, I want it to attach to host. So when I do this now, and when I look at the ports, when I do the Docker, when I run the Docker PS, see, there are no ports shown here, which shows that, okay, it's attaching directly to the network interface itself. If I wanted to inspect the container, I can run a Docker inspect and give the container ID, which is 2336, which will show me all the parameters that are in place concerning this container. So the fact that the container attached to the host, which means it's using the host IP address. So if I were to look at my host IP address, which is this, I can just copy it, paste. Okay, now it's coming. So owners/UI. This is the default. This is the default IP. This is the default port number and how to access owners GUI, which is the Open Network Operating System. Now, what I can do again is, instead of just attaching it to the host, which means now any other Docker container I have can be attached to the host directly using those ports, I can stop the container, list the container, and Docker remove F2. Now, what I want to do in a more programmatic fashion is, instead of just running it like this, I don't want to use this attached host. I want to use port mappings. And what I want to do is, okay, I want to open up the first listing of the port, detects the mapping on the host, and the second listing detects relays to the mapping on the Docker container. What I'm saying is map the 8181 port on the 81, yes, 8181, yeah. Map this port from the Docker container to the same port on the Docker host, on the host machine. I could have given it a different port on the host machine. It's just like port forwarding here. And I also want to map the client port, which is 8101 to 8101. If I was also connecting this ONOS controller to, let's say, a network emulator, an SDN network emulator like Mininet, which communicates through the port 6653, I can map that port here, 6653 to 6653. So now once I run it like this, and I check Docker, inspect 4B, and also one of the benefits of using Docker is, let's say you have a very long ID. Instead of having to write out all the ID Docker, you can, whatever code pertaining to that container, you can map it to the first letters of the ID. So I can go Docker inspect 4B only, and it will know that, okay, I'm referring to this particular container, and it will give me the listings. As you can see, this is the IP address. That the fact that I'm using the default network, which is the bridge network, it just attached me to the Docker network that's created. If I run an ifconfig, you can see that the Docker itself, which is the Docker 0 network here, has the inet, this, netmask, and broadcast. So it means it just attached me to the Docker network. And in this way, all I'll have to do is I can use the private IP, which is this, the IP address, which is this private IP, and just run the ONOS controller using those ports, ONOS/UI, and it will still direct me. But the advantage of this now is the fact that it's not directly attached to the host, but it's attached. It's configured to communicate with a particular port on the host, and this gives you much more flexibility than just attaching those ports directly, just mapping those ports directly to the host ports. There are all other different aspects of Docker, and also it's like, now I've shown how to run the container itself, and then there is this possibility. Okay, let's say someone else wanted to use this container and wanted to have all other dependencies on it. That's where the Docker file comes into play. If I were to show you the, okay. If I were to show you a YAML file here, because I had like a Docker file and an almost ONOS YAML file. If I were to show you the YAML file, okay, VI. Now this is the file that you create, and this is the file that you can run, that will just create the whole image for you. And what this is showing is just configurations. Like from the first thing was, instead of having the whole image, you can send this file, and any person you send this file to, any other technical guy you send this file to, that can just run the file through the Docker Compose app, can just get all the dependencies you have installed without actually necessarily downloading any of them, and it goes directly to its container. So it gives you this flexibility. And this is also version controlled, meaning you can do any edits, you can add anything you want to it, and then post it on your Docker Hub or post it on your GitHub, whereby someone else can download it and run it and get the same configuration Docker container. So not to bore you too much as with all these technical details, this was just a quick recap. This was just a quick intro to Docker, and then the abilities of Docker. And also just to show you, like I said, you could have seen the provisioning of Docker itself, as it takes up quite little time to provision and run a container, instead of having to wait for a VM, installing the Linux operating system on it and running ONOS on top of the Linux operating system, all you need to do with Docker is just run an image. And with this image, it has the barebone Ubuntu Alpine Linux. And also it has all the dependencies needed, like the Java JDK. As you can see, if I showed you the Docker image, you can see the ONOS project has a size of 837 megabit, which comprises of the Linux OS itself, which also comprises of the Java JDK and all the other dependencies needed to run the ONOS project. And then still you can see the provisioning part of it and the running part of it, the removal of all of it is way faster than using a virtual machine. So this was just a quick demo of Docker, and I hope this demo was okay. So I will stop here and ask the audience if they had any questions.
Okay. Thank you very much, Abdoulie, for a very nice talk, very interesting and practical, very practical talk. Thanks a lot. So I'll open the floor to everyone. Yes, okay, you have already have one question. Matthew Rahman is asking, what if we don't have an image pre-built? So you can see the question in chat. Yeah.
Okay, so if you don't have an image pre-built with Docker, it's easy. It's like once you have, let's say you have an Ubuntu operating system that you want to convert into an image, all you need to do is just create a Docker file. Like with that Docker file now, what you do is add all the dependencies you want in the Docker file. Let's say you've already created an application that uses a particular dependencies. Let me show you from here. This Docker file, what you will do is just the minute you can use this Docker file to build an image, you can use the Docker build -t, meaning the target, with this Docker file itself, and then it will be responsible for building an image of all the dependencies that are in this Docker file, like I just showed you earlier. And that converts it, this build command converts that into an image which you can post to Docker Hub itself. So the image part of it has to relate with the fact that you can have an already installed dependencies or already installed applications that you'll be using, and then you can use the build command to create an image from that. I hope that answered your question.
Yeah, okay. So Abdoulie, there is another question from Votha. What is the performance comparison between image pre-built and installed in the virtual machine?
Okay, so just to show you right now, as I am running the ONOS, and even though it's running on its own operating system right now, it's running Ubuntu operating system, and it's the ONOS project, a Java JDK, and we all know how Java is resource extensive. But the fact that it's using the underlying kernel means it's way more lightweight than a virtual machine, because it does not need to create its own guest operating system. It does not need to replicate all the aspects of the operating system, including the kernel, because it can just sit on the underlying kernel of my actual operating system installed on my machine, and then create its own file for system on top of that. So it does not need to create its own kernel. So it's way more faster, and I can whip up, let's say I have one that's running, I can whip up to 5, 6, 7, and you won't see any change in my usability, any change in the usability of the system itself. But it uses very little memory in comparison to virtual machines. And that also shows how fast the provisioning is, because most of the times when you're provisioning a virtual machine, it will take you minutes, if not, yes. But with Docker, it usually takes you just seconds to provision a whole Docker image, which just shows you that, okay, the amount of RAM or the amount of memory it uses, it's particularly less in comparison to virtual machines.
All right. I hope Votha, that answers your question. I think Mati, you can have that question offline with Abdoulie, because Professor Curri is already joined, and I think we should move to our next talk. You can send your questions to me if you want to ask anything from Abdullah, because he's a researcher in our lab here. So I can get hold to him of him anytime, hopefully. Right. So I think it's Abdullah. Once again, thank you very much for your talk. Very interesting and very practical. Thanks a lot. So yeah, I think we should now move to the next talk. Let me my screen for the physical audience to see. How to get an enlarged image of this? No, in fact, why I'm sharing the screen? Sorry, Professor Curri should be sharing the screen. Right, so I'm making Professor Curri co-host so that he can share and start presenting. But before that, a quick intro. Thank you so much, Professor Vittorio. Professor Vittorio Curri is my postdoc advisor. He is my mentor. He is my long-term collaborator. And so we are going to finish the technical talks or technical session of this SDON training event with his keynote speech. So Professor Curri received his MS degree in electrical engineering in 1995 and the scientific doctoral degree in optical communication in 1999 from Politecnico di Torino. He is a founder member of OptCom and Photon Lab. He is currently an associate professor with the Department of Electronics and Telecommunication, Politecnico di Torino. He has been a visiting researcher at Stanford and UC, University of California and at Santa Barbara. His major research interests are in the fiber transmission modeling, including nonlinearities, transmitter and receiver optimization, and advanced modulation formats. Since 1998, Professor Vittorio Curri is an active member in developing software tools for simulation of optical systems. In fact, the first implementation of OptiSim, which is a very famous simulator in the optical community, is being Professor Vittorio Curri was part of that team. So in 2015, Professor Curri started to investigate the impact on physical layer on transparent optical network. I was luckily part of that work when he started doing that in 2014 and 15. I was in Torino, specifically in the open physical layer softwareization, including the AI techniques. And he is the scientific chair of the GNPI project that has been talked about in the last 2 days in the Links demo, because Links was built on top of GNPI, and Professor Curri is the one who is the scientific chair of that GNPI project within the open source consortium of Telecom Infra project. He is also a senior member in also of IEEE and a member of Optical Society of America, and he is a co-author of more than 280 scientific publications, including 2 JLT best paper, and JLT is one of the top venues. So he is a recipient of 2 JLT best papers as well. A Journal of Light Wave Technology by Optical Society of America. So once again, Professor Curri, thank you very much, and buongiorno. Thanks a lot for joining in. It's all yours. Please go ahead. Thank you.
Thank you, Arsalan. Thank you for the kind invitation and the great introduction. Thanks to all. So let me share my screen. And then I will check if you see properly what. Can you see my screen, Arsalan? Hello?
Yes, sir. We can see it.
Full screen.
Yes, sir.
Yes. Okay, thank you very much. So I have time until 10 my time, and so I will try to address all the slides I prepare. So what I'm talking about today is what is the scientific foundation. Hello?
Hello, yeah, Professor, sorry to interrupt. I think there is...
Yeah, let me know what I can do.
We cannot see your full screen. The physical audience present here in NUST cannot see your full screen. I think the PC is not responding for the moment. No, it's not something at your end, because I think
okay, it's your end. Okay.
Yeah,
okay. Let me know when I can start.
Yes, please.
just for the people online, we are waiting. I see that you wrote no audio. No, we are waiting for fixing the issue that they have live, cannot see the slide. So we are waiting for the starting of the presentation. So I guess online you see and listen
Yes,
very
we
well.
can see. Yes, we can see and hear properly. Thank you.
Yeah, let's wait for the clearance for the people attending live.
Okay, Professor, I think it's all good now. Please go ahead, and sorry for the interruption once again. Please go ahead.
No problem, no problem. So we can start now. Okay, thank you again, and then let's go through the slides. So I have only 45 minutes because then I have another meeting, but let's try to address the most important part of this presentation. That will be about what is the model that is behind or inside GMPY, or in general we have to use to abstract and to understand what happens at the physical layer. So the fundamental purpose, so I know that the audience is including, as I seen from the previous presentation, people working at higher layer, at least not exactly on the physical layer, but the purpose is not to force you to become an expert of physical layer, but to show you how we can easily or quite easily operate in order to virtualize the WDM transport function within a software-defined optical networking scenario that, of course, has to be disaggregated and hopefully also open. So, yeah, here is the outline, and then let's go faster. Then the GMPY project, I will just, I guess, Jan Kundrat already introduced the project, and then he is the maintainer of the software. I guess he presented very well what is the software structure and the repository and all this kind of stuff. And so we can skip the part about software and just talking what is the, why is needed the abstraction and where we are located within the telecom infra project working groups. So we are in the physical simulation environment, and we are creating GMPY, that is the abstraction of the physical layer that is used for higher layer working group of the telecom infra project to implement vertically a disaggregated network. So which are the fundamental concepts? So let's start from the need for a physical model. I know that the community networking, let me call it this way, networking community, the community operating starting from layer 3 or layer 2, most of the time assume the physical layer is a commodity, and then is run by the people working on the physical layer, and then you don't have to care about what happens on the physical layer. Someone will take care of it, and you assume it is a commodity. It was the case until, let's say, 10 years ago, when the physical layer was not so much exploited for the optical portion, and for the wireless portion still until 3G, the cellular network was still a closed system. But now we are moving fast toward full exploitation, the need for full exploitation of the physical layer, both in 5G and future 6G, because to take out all this capacity from wireless, you need to optimize the physical layer. And the same on the optical network. We have billions of kilometers of fiber worldwide with the optical infrastructure. That is the supporting all the telecommunication. All the telecommunication is supported by the optical network. And with 5G, optical networking will go up to the fronthaul. You know that the standard that are standard in 5G is difficult to say, but what happens in the world of 5G is that also fronthaul is becoming optical, because there is no way to take out all this capacity without exploiting optical networking or optical transmission. And so because of this, in the overall multi-layer network, the physical layer must be properly addressed. And the request is to be able to virtualize the function in order to be used vertically by the other layer, and then you can fully optimize your network. For instance, for the optical network, we are going towards IP over WDM that, of course, needs a full abstraction of the WDM function. Otherwise, you can manage this function if it is an ossified function inside your network. So let's move to the playground of our activity. That is an optical transparent network. What is an optical? I guess you know very well, but let's try to address which are the fundamental elements of an optical transparent network. Is an infrastructure made of switching nodes and optical lines connecting each switch to the other, each ROADM to the other. And then traffic, and this is the transparent infrastructure where you can deploy traffic as transparent light paths connecting any source to any destination. And so the component for infrastructure are amplifier, fiber, and ROADMs, and then components, network elements to introduce traffic, to deploy optical circuit are transponders, okay, and transceivers inside transponder. Let's consider this. And then the optical, and so what is the networking part at the physical layer? The networking part of the physical layer is, let's see if I can. Okay, the networking part of the physical layer is performed by what? By the transparent deployment of a light path and by the choice of the route established by ROADMs and the choice of the modulation format, the bit rate, the spectral occupation of each optical connection. And then traditionally, the physical layer was developed independently of what you put on the top, and using intensity modulation direct detection, everything was ossified at the beginning of life, at the design phase of the network. Now, with coherent optical technology, you can reconfigure continuously your network, of course, with time constant that are quite long, minutes, but you can reconfigure your network and you can change the light path route. You can progressively load your network, and on transceiver, you can operate on the transceiver to pick the proper modulation format and symbol rate that is the one mostly suitable to the networking scenario, the transmission scenario. You understand that to do all this kind of job, you need to know what happens on the physical layer. You need what we like to call the digital twin of the physical layer, because you put this digital twin inside your network operating system, and so you can virtualize operation on the physical layer. You can slice your physical layer, and then optimizing the exploitation of your optical transparent infrastructure. Exactly what we do on the free space in this big glass cloud that is completely transparent, that is available, are billions and billions of kilometers worldwide. We can implement several, how to say, we have a very large room to optimize the exploitation and to give better services and to reduce prices, to force for the to promote the development of transparent optical network, not just in the richest country worldwide, but everywhere. And this is the part, the purpose of the Telecom project, and enabled by what I'm going to present today. And what is the scenario in terms of disaggregation or aggregation? So to implement an open networking, and for sure, and the software-defined optical networking, we cannot have an aggregated network. That is the status of network, the characteristic of most of the networks that are right now available. An aggregated optical network is an optical network that is single vendor where all the network elements are, how to say, hidden within the control software that is proprietary, that exposes typically a single API that is a request of traffic that is coming for a higher layer, but then you don't have levers available to optimize, to tailor the exploitation of the physical area in the proper way to optimize the performance and to address performance in the proper direction. While we have to move on toward disaggregation for to introduce software-defined optical networking. And disaggregation is full disaggregated network are future-looking, where every network element is open and may be operated by the control plan or the data plan, optical control plan or optical data plan, in order to optimize control and data optical circuits deployment. This, as I say, something quite future-looking. What is a good compromise, and we are moving towards this direction with already many proof of concept and some deployment, also in commercial network, is the partially disaggregated network where the optical line system connecting every ROADM to every ROADM can be a closed system, a single vendor system, and then you access to the transponder, to the ROADM, and to the optical line system controller that is and so in order to implement your networking operation. So let's go in more details in what we mean for partially disaggregated network. A partially disaggregated, of course, this is just 3 ROADM network, but just to make you an example. So we have, we suppose that the line includes also the degree of the connector ROADM. Each line can be a different vendor line that is controlled by a line controller. And then on top of this, that can be independent one from the other. And also we have shown in some experimental proof of concept that can be autonomous, completely working autonomously, just reading from monitors data of your line and putting your amplifier and booster and preamp of ROADM to operate at the optimal working point. So this there is something granted. On top of this, you have a network controller, for instance, ONOS, that talk to the transponders to deploy LiPAT and talk to the ROADM, the switching part of the ROADM, switching matrix of the ROADM, in order to implement the optical data plan and so deploy the LiPAT. Okay, this is the partially disaggregated network scenario. Telecom Infra project is moving this direction, and specifically the MUST working group is working to develop a demo and a proof of concept. So at the very end, what we need to understand how the WDM, the transport scenario, works, and we want to summarize the transport inside a simple metric, a simplified metric that must be the link between the physics and the digital world. Fortunately, the physics using coherent optical technology is in favor of this, and it's been extensively proven in the last 10 years, since when the optical coherent technology was introduced, that each LiPAT can be managed like as an equivalent additive white and Gaussian noise channel, non-linear, but AWGN. And so it is a fundamental characteristic. Why? Because if I have an AWGN channel, I can summarize its behavior by a single parameter, that is the SNR of the channel. In the case of LiPAT, there is no standard, but what seems to be the mostly used language define this SNR like GSNR, generalized SNR, And generalize in front of SNR means that include both the ASI noise and the other noise component that comes from nonlinear crosstalk happens in fiber propagation. That is called NLI. But regardless of the actual label that you put on the SNR, so you have a single SNR. And then, and so the GMPY in general, the abstraction of the physical layer following this approach is based on this assumption. Just to clarify, okay, GMPY is the software, is the library, the digital twin written in Python that we are continuously developing in the telecom infra project. Just to clarify, is not related to a specific mathematical model for the component. The assumption is that everything is Gaussian, is approximated like Gaussian. So let's see how we can model each network element, because we have seen that transparent optical network includes many different network elements. And let's start from the devices generating the optical signal and receiving the optical signal that propagates through the transparent light, but and so is impacted by that AWGN channel with that GSNR. So what is the impact? Because at the very end, when you want to decouple the physical layer from the logical layer, you need a relationship from the physical layer to the logical layer. We have seen that the physical layer is AWGN, and so it has a single metric that is the GSNR. Let's see how we relate this GSNR to the actual performance of optical transceiver. You know that coherent optical technologies are standard multi-level modulation format that also in optical communication were introduced 10 years ago. And so thanks to the IQ modulator available in the transceiver, and thanks to the DSP, we can define transceiver with exploiting multi-level modulation format with dual polarization, and also selecting the modulation format by defining the VP and VQ, the in phase and quadrature driving voltage generated by the DSP at the transmitter side. And so a transceiver, a coherent optical technology transceiver is this one. You have the input data here that are typically coming from many tributaries of gigabit Ethernet up to the bit rate that is suitable for transmission of optical layer, that is 100 gigabit, 400, and already in commercial system 800 gigabit per wavelength, and in the near future, as you have seen from the Akacha announcement, we are going toward 1.2 terabit per second per light per wavelength. And then on the receiver side, we have the structure that is based on the hybrid 90-degree hybrid, and you implement the receiver, the coherent receiver, thanks to the DSP here. The presence of this DSP at the transmitter and receiver is fundamental to introduce the software-defined approach to the modulation format, because when there was only the intensity modulation at 10 gig, no way to do this kind of approach. Now, the transceiver side enable software-defined networking, because you can, down to the physical layer, because you can operate by the control plane on the transceiver and selecting the operational mode of the transmitter and this receiver DSP. And moreover, we know that our channel is that we are interested in is an AWGN channel, actually dual polarization, because the fiber is this. And so what is the performance of a multi-level modulation format with coherent receiver on a channel that is affected by Gaussian noise? Its behavior can be completely characterized from back-to-back characterization, because in back-to-back you can connect transmitter to the receiver, just adding some ASI noise and then verifying what is the prefect BER that you read on your receiver versus the OSNR. And for sure, you will get a curve like this. So the larger the OSNR, the smaller the BER. And so we can fully characterize this red line you can get from the back-to-back. And so this full characterization you can get from the theory, whatever. So it's something that you can know. In general, a transceiver does not include only transmitter and receiver as described before, but also some coding. And so a forward error correction coder and decoder on the receiver side. From a system point of view, so I'm not a coding guy, so I don't want to go into many details on the coding, but from an application scenario, the BR of the payload with respect to the prefect BR is something behaving like this. Different code, different car, but for sure we have something like this. And so we can identify, given the FEC technology, you can identify what is this threshold. You can typically, the coding present a threshold behavior that is not exactly a vertical threshold, but you can approximate in this way. You can, and consequently, you can identify the FEC code by the FEC threshold, that is a BR threshold. If the BR, prefect BR is below the threshold, so everything works properly. If the BR is the prefect BR is exceed that threshold, so the light path is not feasible, you have an out of service. So very, very simple approach, simplified, but from a practical point of view, very effective. And so consequently, when I have a transceiver, for instance, supporting different modulation format, I can characterize the prefect BER versus OSNR in back-to-back for each modulation format, assuming the FEC technology. You can have you define a maximum tolerable BR, a BR threshold, and so from this back-to-back characterization, given the BR threshold, we can summarize the model for the transceiver in which way, as a set of required OSNR that translate to a required GSNR on the transparent light path that enable a certain rate. Of course, by increasing the cardinality of the modulation format, we increase the bit rate that we can deploy on our light path. For instance, the 400ZR Plus presents 4 bit rates, but at 64 gigabaud, you can select 200 gigabit with the QPSK, 300 gigabit per second with the 8 QAM, and then QAM, and then 400 gigabit with 16 QAM, using the same transceiver, the same pluggable, just selecting the control of the modulation format. And so you can characterize in back-to-back, given the threshold, you translate this BR requirement into SNR requirement. And so at the very end, here is the relationship between physical layer. Physical layer is characterized, fully characterized by the GSNR. And so given the GSNR, I get what? The feasible rate I can deploy on that light path. And this is exactly the enabling the abstraction of the physical. If we have other additional penalty, yes, we can have additional penalty. They can be characterized or may come from the vendor of the transceiver. And so additional penalty can be model approximated through this effect. So a shift on the right of the characterization. So you need more GSNR for the light, but if you have some penalty, and then they depend on the implementation of the transceiver, but typically are specified by the vendor. And so the transceiver model from usage of the transceiver in a software-defined optical networking scenario is this table. We just need from the transceiver information like this one: bit rate, symbol rate that defined together with the roll of the spectral occupation, the required GSNR, the maximum tolerable chromatic dispersion, the maximum tolerable PMD, if you have this information. But for sure, you need this information. So you need the vendor exposes through an open data structure, data model, Young model, the characteristic of the transceiver in order to be used in an open environment. So this is quite a trivial request from a scientific and technical point of view. It's a very high barrier from a political point of view, because of course it needs agreement among different vendors and different players. But from a scientific point of view, it's very simple. So let's move to so these are the devices introducing the optical circuit in your network, and then let's see if we can model. And from that side, we understood that okay, we just to deploy light, but on a transparent infrastructure, I need from the infrastructure information, the GSNR, on the chromatic dispersion, on the PMD, probably also on the latency, that is fundamental. Let's see if we can get this information from the network elements. And let's start from the amplifier. So amplifier conceptually are very simple. And then a model for an amplifier is a model that defines the gain for every lambda you are interested in, and the amount of noise for every lambda. Very, very simple from a practical point of view. And so in general, the request for a model of the optical amplifier is the following. So you need something that, given the settings, enable you to evaluate the output power given the input power for every frequency event and the amount of noise introduced. So you need, this is the model of our amplifier. The request for the amplifier. So again, it's something very simple. So if vendor exposes a model, an API that is able to provide this information, so you ask from your network controller, this amplifier, I give you this set of settings. What happens to my signal? So the amplifier answer, everything is very simple. And the request from the physical point of view is very simple. Again, it's just a matter of politics, of vendors be enable exposing this model and also exposing the control commands, the control language that is requested by the device itself. But this is not a theoretical or technological obstacle, it's a political obstacle that we can overcome and is under discussion in on the many tables of the standardization bodies and agencies that are working worldwide. But from a practical point of view, so everything is very simple. From a realistic optical amplifier model is something that supposing as input settings gain and tilt, give you the actual gain, the actual tilt, given the spectral load, all this information that are fundamental to evaluate what happens by the amplifier. And consider that the ASI noise is the main source of impairment in a transparent optical network. So this is the first request, is to put under control your amplifier in your network to properly control the network. Let's go to the other element, that is the fiber. The fiber is a nonlinear medium, okay? And so in principle, all the fibers connected in your transparent network are an entire nonlinear medium and nonlinear system. And so are to be managed, of course, like a whole system that will move all together. Fortunately, even if this nonlinear effect is there, is the care effect in the fiber, is a perturbation, and as we see it can be addressed properly and enable a disaggregated management of all your network element. Because keep in mind that the fiber is, of course, the limiting element, because all the other are disaggregated. The fiber being nonlinear can introduce some, for sure, introduces some degree of dialogue between different network elements. But we see that this degree of dialogue is can be put completely under control. So what we do in analyzing the optical fiber is to consider the wave equation. Thanks to the nature of the coherent dual polarization coherent optical technology that are depolarized signal instead of the coupled nonlinear Schrödinger equation, that is the wave equation for the fiber, we can exploit a simplify and a wave equation that is that you get after polarization average, that is the Manakov equation. If we put in the Manakov equation the nature of the signal that we propagate, that is a WDM signal with a signal component on both polarization, a different frequency, so it's not a generic signal, we are interested in this signal. We put in the Manakov equation that signal form, and we observe that for every channel at every frequency, we can derive its individually the spectral separated Manakov equation, where we have the linear evolution for the channel itself, chromatic dispersion and loss, plus some crosstalk introduced by the nonlinearity. This crosstalk terms can be separated in three families. One is the self-phase modulation, so the effect of the nonlinear effect of each channel on itself. Then you have the cross-phase modulations that are the typical crosstalk, the effect of a side channel on the channel and the test. And then we have the four-way mixing, that is the generation of new energy because of the interaction of four other channels. The method that is used to derive a model for the propagation is the perturbative approach, quite standard. So I go very fast, and then because it is indeed a perturbation. So consider that the Kerr effect is characterized by a nonlinear refractive index N2 that in silica is about 10 to the power of -20 in the unit, to be compared to the standard refractive index, it is 1.5. So this is the difference. So the NLI is a perturbation. The nonlinearity is a perturbation. The issue is that contrary to what happens in standard glass, where propagation light is over 1 centimeter, in the fiber, propagation is over 100,000 of kilometers. And so this linearity, even very weak, becomes important, as to be addressed, and defines this interference that we address to a perturbative approach that is, of course, legitimate. And we want to derive what is the power spectral density of this perturbation. It has been extensively shown that it is practically after the coherent receiver, it is equivalent. It is not equivalent. It is practically a Gaussian additive noise. And so this NLI is a Gaussian additive noise as the ASI noise. And so we can observe that the SNR is the unique parameter defining the performance and of this modulation format. And this SNR is given by two components, the ASI noise accumulating over the light path and the NLI accumulating over the light path. For the AC noise, we just need models for the amplifiers. For the NLI, there are several mathematical models addressing this perturbative approach. What we are interested are, and of course there are very accurate aggregated NLI models that are suitable for point-to-point transmission, where you know everything, spectral load, characteristic of your line, and so on. So in this case, you can afford the problem in a very precise way. But it is not the case of a partially disaggregated network, where you want to address the impact of each network element in terms of impairment, ASI noise, and NLI, independently one of each other, because you don't know in a partially disaggregated network. So vendor A setting amplifier of this orange line, and vendor B, this one, vendor C, this one is not talking to the other. And the light path generated by a pluggable transceiver by vendor D is not able to know in details everything. And moreover, the spectral load of each line depends on the origin and the spectral load of the network at this point. And so no way to follow the exact procedure of considering the NLI in point-to-point, but we approach a disaggregated approach, a GM model approach to the NLI. Fortunately, in the three components generating the NLI, two are compatible with a disaggregated approach. You can see this is a self-channel interference. This is a cross-channel interference, but it's exactly a crosstalk. You can see that is the side channel that impact on the channel and the test. And then you have this for mixing. This for mixing should be a problem, because in this case, we cannot disaggregate the problem. But fortunately, for most of the cases, I guess 99.9% of the deployed fiber has a dispersion larger than 2 picosecond nanometer per kilometer. And so this for mixing is practically negligible. And so fortunately, the physics again is helping us. And so we can address the GSNR, the abstraction of transport, in a disaggregated way. That is this one. So we can approach the GSNR degradation of this separately. So what we need to know from the fiber in order to have an accurate NLI evaluation and GSNR evaluation, we need to know very well the fiber loss versus frequency, and is true more and more important with the expansion of spectral exploitation of the fiber, are fundamental connector losses, and the first connector at the input of the fiber span is very important. And also you need to consider stimulated Raman scattering. That is another important game player with the expansion of the fiber. And moreover, you need to consider the effective area, the variation of dispersion with the frequency, and so on. In terms of fiber loss model, so what we suggest to use is the phenomenological expansion of the loss instead of the polynomial expansion that is not suitable for the fiber, because the fiber includes in the loss 4 different phenomena, and is much better to use this phenomenological expansion. And moreover, you need to solve the stimulating Raman scattering equation in order to have a proper loss profile that includes the intrinsic loss and the effect of stimulating Raman scattering. And then we have this evolution of each light path, of the loss and gain of each light path, and then you can evaluate the NLI in a simple way and very fast in terms of computation. This is the evaluation that we use inside the GMPY. Okay, the last components that network element that we need to address in terms of modeling are ROADMs. ROADMs are a very complex structure if we go up with the degree, but from a propagation point of view, again, are quite simple. So a ROADM is a device that enables any wavelength in the CDC version to be transparently switched from any direction to input to any direction of the output for the express traffic, but also including a degree for adding and dropping. What is the effect of the ROADM? The effect of the ROADM on QoT is quite simple. It introduces a possible filtering penalty that again is a GSNR degradation. It introduces a possible ASI noise if you have some active element inside, and also some possible crosstalk. But everything is addressed by an SNR management. So crosstalk and ASI noise introduce GSNR penalty by introducing more noise, but also filtering penalty can be addressed as a GSNR penalty. So from a conceptual point of view, is very, very simple. Again, from a practical point of view, proper RODAM model needs, again, the collaboration of vendors. First, need to be open to expose its internal characteristic in internal control, but also needs a full characterization of filtering penalty depending on the symbol rate, depending on the modulation format. So it's a large number of possibilities that are conceptually very simple. So it's nothing fancy from a scientific point of view, but on the other hand are a large number of requests that must be satisfied by the vendor or by a third party that is going to give a model for the RODAM, like Telecom Infra project. But this is the request. and the effect of RODAM is becoming more and more important with the flat grid, flex rate approach, and also with a symbol rate that is approaching the channel spacing. And so if you use 32 gigabaud in 50 gigahertz, so no big deal about filtering penalty. If you use 69 gigabaud in 75 channel spacing, so filtering penalty becomes an issue, as well as possible detuning or center wavelength of each filtering element. But again, from a practical point of view, everything is quite simple. So let's put together all this information that the physics in a characteristic of the physics. Let's see if we can build actually what is needed, the digital twin of the optical transport, of the transport layer in the transparent optical network. And this digital twin is there, is quite natural, is a graph as a data structure, where each edge is an optical line connecting switching nodes that are also graph nodes. And we manage for every light path this weighted graph by navigating the graph and by adding up additive metric. For the GSNR, if we are able to identify the GSNR degradation of every line and possible of every crossed node, so we get the overall GSNR by adding the inverse of the GSNR. You know that GSNR adds up in inverse mode, but you can see that you get easily the GSNR on the light band under test. We can also address the filtering penalty, that if it is small, the filtering penalty adds up in dB in this way. And so if you have some software that is able to create this data structure and to navigate this data structure through a software that is a module that is the quality transmission estimator of the lambda under test, and so you get the GSNR from the digital twin. So the digital twin asks to the network controller, to network element, give me your parameter. I fill the digital twin that is the weighted graph, and I navigate it to get virtually all the performance on the physical level. Besides the GSNR is very important, another additive metric that is the latency. Latency in the 5G world is and will be very, very important. And consider that the fiber as not fiber in general, propagation of electromagnetic field is not introducing no latency. Consider that the speed of the electromagnetic field in the vacuum is the speed of light. The speed of the electromagnetic field in the fiber is 2/3 the speed of light. It means that 100 kilometers of fiber introduce about round trip, if I remember, 1 millisecond of latency that is not negligible if you consider that the 5G traffic has some services sub-millisecond of latency. And so a digital twin of your optical infrastructure, including also the latency management, is fundamental. And moreover, you can also accumulate the chromatic dispersion, PND, PDL, all this kind of stuff. And from this digital twin, you can do all the operations. So you get from the network element information, you fill this digital twin together with the status of the network, because of course the NLI depends also on the spectral load, and then the network controller interact with this digital twin to perform all the operation, virtualizing the physical layer. So does it work? So that's very fast, then I have to finish here. Does it work this? Yeah, we have done many GMPY validation. So here is a set of paper. And then, for instance, this is a validation. Sorry, a validation we have done in Microsoft in Seattle, 2 big experiment, and this is the network with a geographical dimension footprint of 2,000 kilometers. Is all in the lab in Seattle of Microsoft. But and what we have done is to characterize the transceiver. So we have done several multi-vendor experiment in back-to-back in this way. And then, and for different light path, we measure the BR, the prefect BR, and we translate the prefect BR to the GSNR, to the measured GSNR using the back-to-back characterization. On the other end, we get the network description and the network status from the network controller, and we have done directly from the Microsoft network controller, SDN controller, this operation. And we have done a manual operation to translate this information into JSON file that is the input of GMPY, and we asked GMPY to estimate the GSNR on the weighted graph that was for this topology. We estimated GSNR on different light paths. And here are the results. So these are the spectral load, full spectral load. This is the picture of this amazing setup that they in Microsoft they have. And then we tested 500 cases with different modulation format, with the different distances, different spectral placement in this spectrum, and so on. And here are the results. So of the measured GSNR and estimated GSNR. You can see that the measurement is always very, very accurate, with an error that is always within 1 dB. And you can see that in this specific case, with some assumption of connector loss at the input, this is the distribution of the error. Error is predicted GSNR by GMPY minus measured from the transceiver. So where is coming from this error? One of the main, sorry, I don't know what happened. Sorry. Everything is moving. Okay. One of the main player in the accuracy of the estimation is the very first component, very first connector in every fiber span. Here is on the same data set, we change the connector, the assumption of the connector loss, and we observe a different distribution. Other source of inaccuracy are ripples of amplifier and filtering effect of on the media channel, on the border. But even in this case, even with all this uncertainty, so we can see that the error in the estimation is always very, very small. It means that we can completely trust with a small request for margin the prediction of GMPY, and so we can use GMPY as a digital twin in this multi-vendor scenario using mixed fiber, mixed amplification, Raman and EDFA amplification to abstract the physical layer. Sorry, I don't know why it's doing this. Okay, we have also done a measurement in the brown field. These are the results on sunlight, but on the core network in the US of Microsoft. And then following exactly the same procedure, we have done the measurement, but in this case, light paths are carrying real data. So is up and running network. You can observe the estimation of GSNR and the measurement. Again, is a very, very an accent, I would say, is almost incredible. This accuracy, and confirming that we can do what we want. And then we have done also a flex read, flex rate evaluation in the Orange lab. Here is the JOCN that we have submitted. We just received the revision, major revision. Actually, I don't know why they asked for major revision. Let me read what happens. And we tested a different symbol rate up to 69 gigabaud in 75. And again, you can observe the excellent accuracy of our prediction. We have done also something on multi-carrier transceiver that we have submitted to SC. Hopefully, they will accept it. And then we have also used GMPY together with ONOS in San Dimo. We have also done an experiment together with Scuola Superiore Sant'Anna that we have submitted to SC using 3 RODAM from Open RODAM from Lumentum, 2 lines with in-house controller, and 2 Cassini for pluggable. And we have an ONOS that is controlling everything. And then we have submitted to OFC again. Let's hope that will be published. And then, okay, I guess I have to finish here because I have another meeting soon. And so I have to skip the other slides. In case, Arsalan, I can share this PDF if someone is interested. You can circulate. Thank you for your kind attention. And then hopefully it has been useful what I presented here. I have 4 minutes left for questions, if any. Hello?
Hello, Arslan. Hi, Professor Curri. I don't know if Arslan has a connection problem. It's me, his collaborator, Mohammad Imran. Thank you very much for your talk. It was really nice. I have just, because you have just 4 minutes, I have this question. You know, the experiments you showed, I see that I only see just one kind of fiber in the experiments, and I couldn't also see.
No, there is also true. We test on yeah, the mixed yeah, I don't
mixed
know.
fibers. Okay.
The test bed from Microsoft was including SMF, True Wave, and ELIF, and
okay.
EDFA and hybrid amplification, and also in the field, in the core network. If I well remember, they look at the ECOC or JOC. The JSM paper are all open, so you can. Read
okay.
it.
Thank you.
You
Yeah,
can,
because my question was, yeah, about the model, that if it also caters different type of fibers, and also the presence of the DCFs, you know, DCM modules in the network, could they also introduce
dispersion
more loss
compensating model? No, it's all in uncompensated network.
Uncompensated. Okay.
Uncompensated network. Uncompensated. Yeah. But in terms of fiber type, we have tested all the fiber type except the zero dispersion wavelength. But you know, this is
that's Italy, rare. Only in Italy and Japan. Yes,
and Japan, correct. Only in Italy. In Mexico, also in Mexico they have some. But the other countries don't have any type of anyone is using this. Was not so smart installing that fiber in 1990s. By the way, they have is installed. And they have,
so just one.
Yeah, please.
Yes. Just one more question. You know, how difficult it is to add a new modulation format and update the model, for example, considering in the probabilistic shaping, you know, for the
our role is modulation format agnostic. So all modulation formats are the same. So what we have observed, you know, that if you do simulation and exact modeling, you see this modulation format dependence. But when that is not so large. So the big difference is between QPSK and 16 QM. And then when you go up with the cardinality, everything is becoming very close to the Gaussian modulation. But when you go on the field, according to our very large experience, and we have tested the model on so many different scenarios, different modulation format, different vendor, shaped constellation. And the last test that we have done is on multi-sat carrier that, you know, there is a single vendor that is making this.
Yes.
And so I don't have to disclose, everyone understand. Then in the field, the prediction is even better than what we observe by simulation, speed step simulation. So my feeling is that the average that you have in the field, because of additional effect, random effect that is in the field, that we summarize in the Monaco equation in our modeling. But in the field, you have to consider that light propagates according to the Kaplan nonlinear Schoen equation, where you have the random birefringence that varies with the frequency according to the Manakov and then Dr. Marcusen and Dr. Menyuk very interesting paper. And then this average, in my opinion, is introducing a further degree of how to say, averaging effect that is moving towards the Gaussian behavior of all practice, most of the practice scenarios. So what we didn't test is a very short reach, two span. So perhaps they are inter-data center connection up to 80 kilometers. Perhaps the model is a little bit pessimistic, and you can observe some modulation format dependence. But in that scenario, you will use the 64 QAM, and the 64 QAM is behaving very similarly to the Gaussian modulation. And the last, you comment on the shaped constellation. We tested shaped constellation in the paper we have submitted to JOCN, and everything is exactly working so well that you are surprised.
Okay, that's great. That's great.
So I strongly believe that you can manage your network using GMPY. The issue is to know the input parameter.
Because
type of fiber.
Yes. In the OA model, when you say if we give these settings, so I was just imagining, how much these settings would vendors would share with us, or would accept.
And also on the fiber type. So
yes,
the fiber under the ground, as I guess there are some operators know everything, the exact fiber type, the exact length, but other operators don't know at all.
Don't know.
They have on the field.
Exactly.
And moreover, it's very important, lumped losses. Connectors, splices are even much more important than the modulation format dependence of NLI.
Yes.
Much more. Reports of amplifiers, all this kind of stuff.
Thank you very much. Thank you.
You are very welcome for your.
Thank you for your wonderful talk, and it was really useful. And hope we will keep on learning. And please share your slides with.
Okay, I'll send to Arsalan my slides. Okay.
Yes.
Okay.
Thank you, sir. Thank you very much.
I have to leave because I have another meeting in a few minutes.
Thanks a lot. Thanks.
Thanks to everyone for
thank you very much,
invitation.
Professor. Thank you. There is some technical problem with the PC. It's hanged up. We heard your entire talk, and we heard the QA session with the Dr. Imran as well. So thank you, Dr. Imran, for saving me at that moment when the PC hanged. So anyway, the physical audience is right here, and I think they have no question. In any case, I mean, you have your meeting right now. So if the physical audience have any question, they can get back to you, Curri@polito.it. I'll share your email address, and they can get back to you by me as well. So once again,
I will share the PDF of these slides.
Yes, the PDF of the slide deck.
Okay.
Yeah,
okay.
Thank you very much for your time.
Thank you to everyone.
Thank you, Lord.
Thank you.
Have a good day in Pakistan. Bye-bye.
All right.
Yeah, walaikum assalam from Pakistan.